Hello, once again, ladies and gentlemen. Dewang Padi here. Welcome back to our PIC assembly language programming tutorial videos. On this particular video, titled PIC assembly language programming in a nutshell, basically here I'm going to try and cover most of the important aspects when it comes to PIC assembly language programming. Right. I'm going to use an example to try and demonstrate the most important things you need to know so that you are able to write a PIC assembly program to achieve a specific function. Right. So in this video, we are going to use the PIC16F88 microcontroller, and we are going to look at its hardware, the referrals and features. We're going to look at its memory and special function registers, and then we're going to look at the assembly instructions. Now, the assembly instructions that we're going to look at apply across all 8-bit microcontrollers. These instructions can be used for any 8-bit microcontroller, PIC12, PIC16, and PIC18 microcontrollers. These instructions are still useful on all of them. Right. So after looking at the hardware, special function registers, and instructions, we're going to use those to write an assembly language program to achieve a particular function. In this case, I have an example program that I want us to look at. Right. So in the very first tutorial video I released on PIC assembly language programming, I did discuss this very important point to note. For you to program any microcontroller, your PIC microcontroller in assembly language, you first need to know the particular hardware you want to control. You need to know your microcontroller, its pinout, functions, and capabilities. Then you need also to know its memory organization and special function registers, because these are the registers you use to control the hardware. And then you need to also learn your assembly instructions, because you use these assembly instructions, together with your special function registers to configure and control your microcontroller. You need to know these three so that you can get started with assembly language programming. But in this case, you don't need to memorize and know these things by heart. You need to learn them as you write a program. That's the only way to learn programming. You don't go and read the whole data sheet from page 1 to the last page. It won't make sense. A data sheet for any microcontroller is used as a reference manual to refer to it so that you can know how to use a specific feature or a specific function of that microcontroller. Right. Now, how are you supposed to learn these things? Given a project or an example, you need to familiarize yourself with the hardware of that particular project or that particular PIC if it is being stated for you. Familiarize yourself with the hardware. Look at what is required of you in the example. Check which special function registers are required to achieve that. And obviously, you have to use assembly instructions with those special function registers to control your hardware so that it achieves what is required of you. So we're going to apply this principle in almost any assembly language programming for the PIC microcontrollers, whether you are aware or not, but this is basically what it means. Right. Let's look at our PIC16F88 because that's what we're going to use. Mostly the things to note here is that your PIC16F88 has 16 I/O pins, 8 on port A and 8 on port B, right? And on port A, RA5 is an input-only pin. So one of the things you will learn as you familiarize yourself with the PIC hardware is that you need to know the capabilities of each and every pin. RA5 is an input-only pin if you use it as an input pin, or it can be used as an M-clear or a reset pin for your microcontroller. This pin can never be configured and used as an output. You never connect an output to RA5, right? Other things to note is that most of port A pins come with analog capabilities. RA0 to RA4, they have analog capabilities, and also B6 and B7 have analog capabilities. This PIC microcontroller, on default, it comes with analogs enabled. On default, these PICs, which have ADC capability, are on default analog pins. If you want to use them as digital pins, you will have to disable that analog because it comes enabled on default, right? So that's a few things to note or to know about your microcontroller, depending on what is it that you want to do and what is it that you need enabled or disabled. Then from knowing your microcontroller, its hardware and capabilities in terms of its hardware, then you go and look at special function registers necessary for your application. You don't need to learn all of them or know all of them by heart. You will always refer to these registers whenever you program your microcontroller. But the more you program, the more familiar you get with these registers. At some point, you might not need to refer once you have written too many programs or enough programs. Right. Depending on the application, you will most of the time surely make use of trace registers and port registers and the status register to switch between the banks, because you need to access registers in different banks. So status, ports, and trace registers are the most obvious ones you will use. The uncell register, even if you're not using analogs, you might have to go access the uncell register to disable analogs, because the analog capable pins on default, they come as analog pins, right? So you come and access uncell, disable analogs, then you can use those pins as digital pins, either inputs or outputs. Right. So we're going to look at certain special function registers through the example that we're going to do. Now, after special function registers, the next thing is your assembly instructions. For the 8-bit microcontrollers, we have 35 assembly instructions. Specifically for the PIC-12 and the PIC-16 series, is 35 assembly instructions, right? These assembly instructions can be used for any 8-bit microcontroller. They will still be valid and functional. Now, with only these 35 assembly instructions, you can achieve almost anything. You can write a program to achieve almost anything. And I'm going to try and make use of most of these instructions in this example. Let's just see what the example is about. The problem says here, draw a schematic diagram, flowchart, and write an assembly program to do the following. Use the PIC16 F88 and LM35 temperature sensor to measure temperature and display it on 2-digit 7-segment at 1-second intervals. Here it means measure temperature at 1-second intervals and display it on a 2-digit 7-segment, right? If the temperature is less than 16 degrees Celsius, switch on the heater on RA1. And if the temperature is greater than 27 degrees Celsius, switch on the fan on RA2. If the temperature is between 16 and 27, meaning if it is greater than 16 and less than 27, switch both the heater and the fan off. Right. When RB0 interrupt occurs, write the current 2-digit temperature value to EEPROM memory and increment address. So the PIC has 256 bytes of EEPROM memory. So when RB0 interrupt occurs, write the 2-digit temperature value to EEPROM memory and increment the address, right? Start from EEPROM memory address 0 and overwrite the old readings once you reach the 256 bytes, right? Meaning after 266 bytes, go back and write again from address 0, overwrite the old data. Use 4 megahertz internal oscillator and make use of watchdog timer to reset the system if it gets stuck or if the watchdog timer is not cleared for more than 4 seconds. Right. So this is what is expected of us. Let's see how one can approach this problem. If you are very fluent with assembly language programming, this might not be a big problem for you. But as a beginner, you might need to break it down into pieces. Small pieces that you can easily achieve and put together. Right. But the first thing to do whenever given any problem that has to do with you writing a program, you need to know what is it that you are writing a program for. There's no way you'll start writing a program with the PIC16F88 and an LM35 temperature sensor to measure temperature in display without having a circuit. Because your program will be directed by how the circuit is connected. Right. So the first thing to do is always get your schematic diagram first. That's the first thing to do. Draw your circuit first. How is everything going to be connected? Before you can even write a program, you need to know and have your circuit in place. Then to write a program, you make use of flowcharts. Flowchart helps you know that what is the next step, and up until the whole part is achieved. After you have these two, first the schematic, then the flowchart, then you can start writing. You don't just start writing from just an example. You need to know your schematic, you need to have your schematic diagram, draw a flowchart as to how the program is going to work systematically, step by step, and then you can go and implement this flowchart in your assembly language. Right, so let's get the circuit diagram. LM35 as an input sensor, it gives you analog output connected on RA0 because RA0 is capable of performing ADC. And then RA1, as indicated there, you are supposed to connect the heater. I've just shown you how you can connect a relay and connect maybe the heater as the load on the relay. And RA2 is for your fan, RA1 is for the heater, RA2 is for the fan. I've shown here how you can connect a motor or a fan. Here an example of a 12 volts fan or motor. I could have also on RA2 connected a relay and then you will drive your fan with a relay. Here I was just showing how you can connect different loads to your microcontroller. Right. And then RB0 must be an input so that when you generate an interrupt through the switch there, you can internally save your temperature readings in the EEPROM, right? Empty, I'm not going to use it, so I'm just going to pull it high. I'm not going to use it as an input, leave it as an empty reset and then just pull it high. 2-digit 7-segment display multiplexed through RA6 and RA7. That's my hardware. Now I need to try and implement that problem. implement a solution for that problem. I need to get a flowchart. But that is a very, very big problem. One has to break it down, at least to say, where am I going to start? To do that, I'm just going to break it down in few steps, or in a number of steps. First thing, go and configure or set the internal oscillator in the configuration bits, and then configure my internal oscillator to run at 4 megahertz. To do that, I'm going to have to look at the OSCON register, oscillator control register, and then go configure my watchdog timer to time out at 4 seconds if not cleared, and then create a 7-segment multiplexing program. And then after creating a 7-segment multiplexing program where I'm using lookup tables to display on a 7-segment, I can then go and implement a 1-second interval, either using one of the timers, timer 0, 1, or 2, generate a 1-second interval program, and then add this program to the 7-segment program. And then go and configure RA0. I'm doing this individually. I can later put them together, or I can do this, do that and put them together, do this and put it here, do that, put it here, add it bit by bit up until you receive the whole, or you achieve the whole requirement. So the next will be writing an ADC program where RA0 is an analog input. You will set your VDD and your VSS as ground, perform ADC and get the temperature reading. Then after that, you still have to do RB0 interrupt. So you're going to do the RB0 interrupt part, where here I can choose the rising or falling edge. We can go and write data on EEPROM whenever we get an interrupt. So these are sort of individual programs that one can write and then at the end of the day, put them together. The last part there will be in the main program. I will then constantly check the temperature. If it is less than 16 degrees or greater than 27 degrees, depending on that, switch on the heater or the fan, or switch them both off if it is in between, right? So these are small steps, individual programs that one has to write and then put them together so that you can achieve the whole goal required of you, which was asked here. Right. So that's what we need to do. This is our hard work. Where do we start? We can start at saying set up configuration bits, set up internal oscillator to run at 4 megahertz, and configure watchdog time. These three, we can make them one because they are quite very easy. I'll show you how we do all of these things. Right. Before we do that, there's just one thing that one has to know. When you write your assembly language program. Now, when you program your microcontroller, whatever you have written in your assembly language is going to be saved in the PIC's program memory in the same sequence as your assembly instructions. Meaning whatever you have written is going to be copied and saved in the assembly, in the PIC program memory. Right, but obviously it will be in machine language, not in assembly language anymore. What the CPU does, the CPU, once the program is saved in the program memory, and you power your CPU, where your CPU will go to the reset vector, which is program memory address 0, start executing instructions from that address. That's why we say origin 00 at the beginning. So the CPU will go to program address 0, start executing instructions from that address, and is going to execute these instructions sequentially according to how you have written them. So the PIC will execute the instructions sequentially from top to bottom, one instruction at a time, step by step, with an exception of branching or conditional instructions. So the instructions are always executed sequentially from top to bottom, with an exception of branching or conditional instructions. Branching instructions go to instructs the PIC to jump. Now, that's when the CPU will only not follow the sequence from top to bottom. Then it will be forced or required to jump through a branching instruction. So when you write your program, in mind, you keep that your program is executed sequentially from top to bottom, with an exception of branching or conditional instructions. So your branching instructions will be a call instruction, a go-to instruction. They force the CPU to jump from one part of the program to the other. Without these instructions, the PIC will continue sequentially from top to bottom. Now, conditional instructions: skip if set, skip if clear, skip if zero. These are conditional instructions. They skip only as your CPU execute instructions and you come across this instruction that says skip if set, and indeed the condition is true, that particular thing you are testing is set, the CPU will skip only one instruction. And after skipping that instruction, it continues sequentially, line by line, step by step, until it comes across another conditional instruction or a branching instruction, which will make it deviate from a sequential execution of instructions. Keep that in mind as you write your program. Now, I've explained about the conditional instructions, your go-to and your call. The difference between a go-to and a go-to instructs the CPU to jump from one part of the program to the other without having to go back. It will only go back through the sequence. But if you jump from one part of the program to other using a go-to instruction, it doesn't really have to go back. You can jump up and down as you wish when you use a go-to instruction. But now, with a call instruction, a call forces the CPU to jump to a certain part of your program, executes that part, and with a call, it always have to come back where it was before the call or after a call. After a call, it has to continue under that call instruction when it returns. With a call, you always have to return. With a go-to, you don't have to return. But both a call and a go-to forces the CPU to leave the sequence execution of program, jump to a certain part of the program. With a call, you have to come back. With a go-to, you don't have to come back. So, with that in mind, let's see now and start implementing our solution. I want us to do the first three parts. Let us try and do the first three parts. For any assembly instruction or for any assembly program, you will have to state in your program which PIC microcontroller you are using. So in this case, we are using the PIC 16F88. So I'm going to say list P equals to 16F88 to inform the compiler that we are using the PIC 16F88 microcontroller. And now the next instruction is to make use of the P16F88.inc file. This file has the names of all special function registers and their bits defined for us. We don't have to define the names of the special function registers like the trace A, port A, trace B, status. They are all defined in that file. We just include it in this program so that we make use of it. Now, for any program that you do, obviously you will start at origin 00 or x00. This will be the start in your flowchart, right? I haven't done that yet because I want us first to look at what is it that we want to achieve. In this case, it is it is configuring. We don't really need a flowchart to do configuration because all that we need to do is configure it. In which way? we want to use internal oscillator, and at some point we also want to use watchdog timer. So let's see what configuration bits, or how we have to set up our configuration bits to achieve that. I've already selected the PIC 16F88 as my microcontroller. So if I go to configure, you can select the device here. In my case, it's already 16F88. Then I can just go configuration bits. And under configuration bits, I can select here. I want to use internal oscillator, internal RC oscillator, where I have IO function on both RA6 and RA7. I'm going to choose that option. Watchdog timer, enabled or disabled. I want to enable watchdog timer because I'm going to use it in this application. Now, power up timer. This one, for now, let's not worry about it. You can leave it disabled, you can enable it, it's up to you, because I didn't cover it in this example. RA5, let's use it as mClear because I've tied it to VDD. It's fine. Brownout reset, disable this. RB3 is connected to the 7 segment. I want to use it as an IO digital pin. Choose that. Code protection off. The rest of those, just leave them as they are. Now, this is the configuration that we need. Now, you set up your configuration bits like that. That should be fine. Right, I'm done with the configuration bits. Now, I need to go then and say, what is it that I need to do next? According to the example, what I need to do next is configure my internal oscillator to run at 4 megahertz. I've said in my configuration bits I'm going to use 4 megahertz, right? So let us see how you're going to do that. Let us see how you're going to achieve that. Go back to the program. I need to go and configure my PIC microcontroller to work at 4 megahertz. I haven't actually drawn a plan on how that is going to happen. So let us quickly do that. A flowchart for configuring my oscillator to run at 4 megahertz. That will be the simplest flowchart you will ever draw. I want to draw, so let's just go to draw IO. Easily draw a flowchart that will enable me to let's say I want to save on device blank. I can just save it. See it's flowchart. Create the flowchart, and then obviously all the time, every time you have your start, which is your origin 0 0, and then the next thing is go and initialize, right? Go and initialize. At initialize here, the first thing I want to do is your internal oscillator must be set at 4 megahertz. I want to go and start configuring my oscillator at 4 megahertz. That will be the only thing to do, the first thing to do. Now, from origin 0 0, what I need to go is configure my oscillator speed to be at 4 megahertz. Right. So let's see then, how do I have to do it? How do I do it in the program? Origin 0 0, that's the reset vector. Reset vector, which is your start in your, I like doing this, I don't know. start in your flowchart, right? So where do we do? Go to initialize. Because initialize, if you say go to initialize, it's a label you need to declare where your initialize is. So I'm going to put initialize there. In this application, I don't really even need this instruction, go to initialize, because I have nothing between go to and initialize itself. I can just have initialize underneath. But if I'm going to put a program between initialize and the go to, then or the reset vector, then I need that go to there. I know I'm going to need it. I already have it there. You'll see why I have that go to there. At initialize, I need to go and configure my oscillator to run at 4 megahertz. So now, to do that, there's just something that you now need to know. Your internal oscillator, you can configure it through a special function register named the OSCON register, oscillator control register. That is the register we need to go and access and configure or write to it so that we can configure our frequency, our oscillator frequency to be 4 megahertz. This register is in bank 1. And remember, go to bank 1, we make use of the status register. So that's basically what we need to do. The status register is a special function register, and it has 8 bits, bit 0 to bit 7. All registers in this microcontroller are 8-bit registers. And now bit 5 and 6, RP0 and RP1, are used to switch between the banks when you do direct addressing. I might do an example of indirect addressing later on, but for now we'll be using direct addressing. So I'm going to switch between the banks using bit 5 and bit 6. Bit 5 has to be 0 and bit 6 has to be 0 for you to be in bank 1. Looking at our memory organization, the 3 different banks, bank 0, bank 1, bank 2. Oscillator control register is in bank 1. To go to bank 1, bit 6 must be cleared and bit 5 must be set. Right. That's what I need to go. Switch to bank 1. I need to switch to bank 1. On default, I think the PIC comes already in bank 0. I can switch to bank 1 by just setting bit 5. Because bit 6 will already be 0. But to make sure that the program, or to ensure that I'm exactly in the correct bank, besides the default reset status of the PIC, I'm in any way going to clear RP1, which is bit 6, and bit set file status RP0, set bit 5. Right. RP0 and RP1, those are just the names for the bit number, bit 6 and bit 5 of the status register. Right. Now, you see, they say bit 6 and bit 5. RP1 for bit 6, RP0 for bit 5. I could have said status comma 5 or status comma 6. Will still be the same as status comma RP1 and status comma RP6. After clearing bit 6 and setting bit 5, it means now I'm in bank 1. I now need to access the OSCON register. I'm now in bank 1 here. I now need to access the OSCON register. And the OSCON register has to, or what I need to do is I need to configure the OSCON register in such a way that it configures my internal oscillator to be 4 megahertz. So this is your OSCON register, oscillator control register. In bank 1, it has 8 bits like all registers in this PIC microcontroller. You can select the frequency at which you want your internal oscillator to run at using bit 4 to bit 6. Right. Bit 7 is there, but it's unused, always 0. So obviously now, if bit 7 is 0, I need bit 6 to bit 4 to be 110. In hexadecimal, 0, 1, 1, 0, that will be 6. The 4 upper bits of this 8-bit becomes 6 in hexadecimal. And then what are the 4 lower bits saying? Oscillator startup timeout status bit. This is a status bit. It will be controlled by the hardware after the oscillator startup. This we can always make it 0, it's fine. Okay, no, this, let's make it 1. We want to run from primary system clock. Okay, this one we're going to make it 1. And then oscillator frequency stable bit. Whether it's stable or not, the CPU will handle, or the CPU will inform you through this bit. We can assume that it is stable and make that bit 1. Doesn't really matter what we do to it. The CPU controls this bit, right? And now the oscillator configuration, where our oscillator is going to come from. Let's use, because now in the configuration bit we said we're using internal oscillator. Let's assign this to the configuration bits, and then the configuration bits will say still we are using the internal oscillator, right? So we are assigning the selection of the oscillator to configuration bits which assigned the internal oscillator already. So our number is going to be 6, the 4 upper bits, and then this 1, 1, 0, 0. 6C. Let me just do it in assembly here. Move electoral value into W. In binary, that value will be 0, 1, 1, 0 for the 4 upper bits, and then 1, 1, 0, 0 for the 4 lower bits. In hexadecimal, this number, it is 6C, right? This is the value that we must move into the OSCON register, oscillator control register. Now, after moving that value into the oscillator control register, then it means we've configured our internal oscillator to run at 4 megahertz. There's another oscillator, or there's another register associated with the internal oscillator, where after setting the speed, you can tune it to plus minus 12.5% using the OS-tune register. I don't want to tune my frequency. I want to use the center frequency as it is without tuning it. You will tune your frequency if you want to recalibrate or calibrate your center frequency, right? If your application are time sensitive and your frequency is not exactly 4 megahertz, it's not exact, the center frequency is not exactly 4 megahertz. In this case, knowing that this comes calibrated, I will assume that the center frequency is exactly 4 megahertz, right? Now, with that said, it means now I have successfully now configured my internal oscillator to run at 4 megahertz. Now, the next thing to do is the watchdog time. What is watchdog time? Watchdog timer is the internal timer in the microcontroller that will increment automatically as your program runs. It will increment, and if it reaches a predetermined time without it being reset, without clearing it, it will cause a reset. It will cause your microcontroller to reset. In this case, we need to configure watchdog timer so that it can reset the program or the PIC in 4 seconds if we don't clear it within 4 seconds. Watchdog timer is used basically in microcontroller systems to prevent the system from being stuck forever. Let's say something is wrong in the program is no longer running the way it's supposed to be, and it is stuck in a certain section. And then it can be stuck in that section for 4 seconds. And if it gets stuck for more than 4 seconds, then the system will automatically reset. It doesn't mean it will solve that problem, but at least the system will still be functional. some parts of the system will still be functional up until one has figured out what is causing the problem on that section of the program and solve it. The watchdog timer is useful to ensure that the system never gets stuck. If it gets stuck, it automatically resets so that at least minimum functions that are functioning correctly can still continue to function. Because if it gets stuck and nothing else works, the whole system will require either a technician or someone who knows to come and reset it, or even the end user to manually reset it all the time. Maybe by removing power and putting power back. You don't want that kind of errors or issues with your devices or systems as a developer, right? So you use watchdog timer to reset a system if it is stuck for more than 4 seconds in a particular location where you haven't found out what the problem is, or you haven't even realized that there's a problem there. Right, so let's now configure the watchdog timer. Watchdog timer is configured in the watchdog timer register. In which bank is that register? Let's see. In the data sheet, it's easy. Here I've already copied most important parts, and the watchdog timer is in bank 2, right? Watchdog timer is in bank 2. The way you'll approach this, the data sheet is the most important tool you will use for this referral. Say now you need to make use of watchdog timer, right? Now, if you want to make use of watchdog timer, and you have your data sheet, you will just scroll down to the watchdog timer site. You don't have to read the data sheet as it is. This is a referral tool. We go to the watchdog timer if there is a topic specifically on watchdog timer. So let's see. If there isn't, then watchdog timer will be covered in special features of the CPU. Let's go to special features of the CPU, and then we want to look at watchdog timer. You don't have to read the data sheet as it is the whole of it. You just need to consult the section you want. I want the watchdog timer. Let's see if watchdog timer is here. Interrupts again, watchdog timer. Now, to do the watchdog timer, you can learn a little bit about the watchdog timer, how it works, blah, blah, blah. I already know that. I'm going to show you how to use it. It's very important that you go and learn and be able to use it yourself. Right. We're going to look at the watchdog timer control register, which is available now in bank 2. Because in our configuration bit, we set enable watchdog timer. What we're going to do in this register is to set the rate or the timing for the watchdog timer, right? So we need to set a 4 seconds. We need to set a 4 seconds loop for our watchdog timer, right? Now, when you read a bit about watchdog timer, we will find out that it can give a timeout of, I think, 2 seconds. 1 millisecond to 2 seconds. Okay, that is the maximum time we can get for this watchdog timer. Given the time-based used for the time nominal range of 1 millisecond to 2 seconds. So for this particular microcontroller, our watchdog timer will reset at a maximum of 2 seconds. We can set it to a maximum of 2 seconds, and then that will be the worst case scenario. We'll have to use this one. We can never achieve a 4 second. So I'm just going to choose the 2 seconds, the maximum time available for this watchdog timer rate, right? So the 2 seconds will be achieved if we set our watchdog timer period select bits to be 1:65,536. because the only available time is between 1 millisecond to 2.092 milliseconds. Depending on the PIC which you are using, the available times will differ. And the PIC 18 series can give even more than up to more than a minute of time. I said 4 seconds because I thought also this PIC can give more than 2 seconds, but it appears that maximum time you can get for the watchdog timer for this microcontroller is 2 seconds. So that 4 seconds is going to change now to 2 seconds. And now to control our watchdog timer or to configure our watchdog timer, the watchdog timer control register in bank 2, we have to move a value in it. Watchdog timer is turned on. Of course, we need to turn on watchdog timer. Bit 0 will be 1. Bit 5, 6, and 7 are unused. They are all going to be 0. So what value are we going to have? 0, 0, 0 for the upper 3 bits. 1, that gives us 1 in the upper 4 bits. 0, 1, 1, 1. So that is 1, 7 in hexadecimal. In binary, what we need to move into the into the watchdog timer control register. But the watchdog timer control register is in bank 2. So we need to go to bank 2. Bit set file, status RP1, bit 6 must be set of the status. Bit clear file, status RP0. That will take us into bank 2. Now we are in bank 2. We want to move a value in the watchdog timer control register. Move a literal value into W. The value will be bit 5, 6, and 7 are unused, always 0. 5, 6, 7, always 0. Right. And bit 4 is 1. So we're going to have 1, 0, 1, 1, and then watchdog timer is enabled. So that will be 1. So 1, 0, 1, 1, 1. That's the value that we need to move into our watchdog timer control register. Move W to 5. The watchdog, what is the name or how is it written? Watchdog timer control register. Watchdog timer control register. Now, this has set our watchdog timer time out to 2.09. Is it 96 seconds? Is it 2.0? What did they say here? 2.097 seconds. That's our, we can achieve a 4 seconds. The maximum we can get for this microcontroller is the 2.097 seconds. Right. So according to our problem, what have we achieved this for? We now managed to set our configuration bits to select internal oscillator, set the internal oscillator to 4 megahertz, and unfortunately we couldn't achieve a time period of 4 seconds for this watchdog timer. The maximum available is 2.097 seconds. We set to maximum of 2.097 seconds. Right. Now we want to go and do this. Create lookup table for the 7-segment display. Write a program that will display on 2 7-segments, 7-segment multiplexing using the lookup table. So we're gonna do multiplexing and then we're gonna display on those 7 segments using the lookup table we just created. Now, use any of the available timer interrupts to achieve multiplexing. In this PIC, we have timer 1, 2, or 3, so you can use any of them. When we perform our timing, we should just remember that we are running at 4 megahertz crystal oscillator. Internal oscillator actually. So now this is what we need to do. 7-segment multiplexing. There's already a video on 7-segment multiplexing, but I'm just gonna go through that part again, but not in details as I did on the 7-segment multiplexing video. I need to show you how we need to add this program together bit by bit. Now we're gonna need now a lookup table, or not a lookup table. Of course, we're going to create a lookup table value, but we're going to need a flow chart to show how we are going to implement this program, right? So let's go to the flow chart where we now need to do 7-segment multiplexing, 2 7-segment multiplexing with a lookup table to display on the 7-segment. Now, I will choose to use timer 0 for the 7-segment multiplexing. You can choose to use any of the timers. Here I've decided to do 7-segment multiplexing using interrupts instead. You could have used any other way to do 7-segment multiplexing. You don't have to use interrupts. You can, in the main program, do 7-segment multiplexing. I'm going to use interrupts, and I'm going to use timer 0 interrupt for this application. Now, to achieve 7-segment multiplexing, it's basically displaying on one 7-segment at a time, but at switching between the two at a very high rate so that the eye doesn't catch which 7-segment is on. They both appear as if they are on at the same time. Right. That's what we need to go and achieve. Let's see now how we have to do that, or how are we going to do that. Go back to our program. This is the program we did. Now, what I can add here as well is that we also did set up our watchdog timer to time out at 2.097 seconds. Right. We now need to go and do a 7-segment multiplexing. 7-segment multiplexing. What do we need to do on the 7-segment multiplexing? And just gonna do it this way. We're still gonna have origin 00 start, but in this case, at initialize, what is it that we want to do? For the 7-segment, obviously, port B must be outputs, right? And then in our application on the second, RA6 and RA7 are the 2 pins that selects which 7-segment is on at a time. So RA6 and RA7 must be outputs, right? And then, because I'm going to use timer 0 interrupts, I need to perform timer 0 calculations to say, after how long will I have an interrupt, so that each and every interrupt I can go switch between the 7 segments, right? The timing I can decide, but the timing has to be so small that the eye won't be able to catch it. If I switch between the 2 7 segments, at 1 second, the eye will see that you are switching between the 7 segments. Only one 7-segment is on at a time. And then that won't really display a constant 2-digit number. To display a constant 2-digit number, I need to create a timer 0 interrupt of a very small timeout. Let's just say something between 100 microseconds to 1 millisecond. I can choose any of those two. Let me start, or let me just use 100, not 100 milliseconds, 100 microseconds to 1 millisecond. So 100 microseconds timer 0 interrupt. So basically in the timer 0, what I need to do is go perform calculations, then find out what is that I need to get 100 microseconds delay, and then set up timer 0 interrupt so that at every 100 microseconds I get an interrupt. Right. After that, the next thing is I'm going to do nothing. And then here I can see endless loop if one wishes. Endless loop. Now I go into an endless loop, meaning just main, go to main there. I've set up my timer 0 interrupt. When I get an interrupt, interrupt service routine, origin 04. When I get an interrupt, I have timer 0 interrupt. When I get an interrupt, I need now to check which 7 segment is on. I just need to toggle between the 2 7 segments. So I will say in my program, I think maybe the easy thing is to put it in general terms. Or let me rather put it step by step, because it's very important that you understand those steps. When I get an interrupt, I'm going to say, first of all, check which 7 segment is on. Is it RA0 or RA1? RA6 or RA7? Which 7 segment is on? Is it RA6 or RA7? Let me just verify now which RA6 is for the first 7 segment, RA7 is for the second 7 segment. Now I need to say, I'm going to start with RA6. Say RA6 is RA6 is RA6 on? Is RA6 on? If RA6 is on, then I know currently I'm displaying on the first 7 segment. I need to go switch to the second 7 segment. So if RA6 is on, this is what I'm going to do. In a number of steps, this is what I'm going to do. Disable RA6, switch off RA6, right? Display data for the second 7 segment, for the second display, and then enable RA7. Enable RA7. That's what I have to do. If RA6 is on, disable RA6, get the data for the second 7 segment and display it on port B, and then enable the second 7 segment. Right. But if RA6 was not on, then it means RA7 was the one that was on. Right? I'm assuming now if RA6 is not on, then it means RA7 was on. Just going to do the opposite. So what's going to happen here is, what am I doing? Right, in any case, I'm going to come to this direction and say, here, what is that I need? I need to now disable RA7 display data for the first 7 segments, and then enable RA6, and then this will happen at 100 microsecond intervals, because you'll have an interrupt taking place every 100 microseconds according to your timer 0 seconds. And then every time you do this, you always have to return from interrupt. So I'm just gonna come here. Before you return from interrupt, you clear interrupt flag. Always clear the interrupt flag. Clear timer 0. Interrupt flag. And then return from interrupt. Right. Both of them are going to do this. It doesn't want to do it this way. Right. Both of them are now going to do it. So this is basically what the interrupt service routine is going to do. Check which service segment is enabled. If yes, if RA6 is on, then we go disable RA6. We move data for the second segment, we enable RA7. Else, if RA6 was not on, meaning it was the RA7 that was on, we disable RA7, put data for the first segment, enable RA6. That's what is going to happen. How do we set up the 100 microseconds time for the timer 0 to set up the interrupt? Now, timer 0 is concerned with calculations that one has to perform so that we can get that 100 microseconds. Let's see how one can achieve that. Timer 0, if configured, or when configured as an internal timer, it runs from the internal oscillator. So you'll say the frequency or the time per cycle of your timer 0 will be equals to 1 divided by frequency at which the timer is running. 1 divided by the frequency at which the timer is running. The timer is running at the same rate at which the instructions are being executed. And the instructions are executed at a quarter of the oscillator frequency. So a quarter of the oscillator frequency will be your F oscillator divided by 4, right? And then that will mean that your timer 0 is running at 1 divided by your F oscillator is 4 megahertz. Divide by 4, right? And then this will be equals to 1 divided by 4 megahertz divided by 4 becomes 1 megahertz. Your oscillator is running at 1 divided by 1 megahertz, which is 1 microsecond. Your timer 0 is running at 1 microsecond. Right. This is with a prescaler of 1:1. That's our timer 0 calculation with a prescaler of 1:1. Now, at timer 0 can count from 0 up to 256. Right. Our timer 0 can count from 0 up to 256. And now for timer 0, we have a register named timer 0 in bank 0. This timer holds a value. This register holds an 8-bit value of the timer 0. And that value can be anything between 0 and 255. Timer 0 is an 8-bit timer where the timer 0 register in bank 0 holds the count value of the timer 0. That can be anything between 0 and 255. Right. When the value has to exceed 256, timer 0, we say it overflows. Instead of going to 256, it goes back to 0 because this is an 8-bit register, right? And we say it overflows. So when it overflows, it generates what we call timer 0 overflow interrupt. That's what we're going to use. But we want it to interrupt at 100 microseconds. So to get 100 microseconds, if our single count, time per count, if our single count is 1 microsecond and timer 0 can give us a maximum of 255 counts, to get 100 microseconds, we just need 100 counts. But this overflows at 256. So what is that we are going to do? We say because now we need 100 microseconds, 100 microseconds will be equals to 100 counts. There's no need for calculation for that. But if you want calculations, what you will do is your required number of counts given a prescaler of 1 and your time per count being 1 microsecond, you say your required delay divided by the time per count. So your required delay is 100 microseconds and your time per count is 1 microsecond. Now your required number of counts will be 100 counts. Right. Now, because your timer 0, it makes a revolution. Your timer 0 will start from 0. 0 there, 1, 2, and so on, up until 255. When it goes to 256, it actually goes back to 0. And this is when it generates an interrupt. This is when it overflows. So it overflows when 255, instead of going to 256, it goes to 0. Now we want the interrupt here to take place exactly after 100 microseconds, not 256 microseconds, because if the time per count is 256 and we start at 0, this is going to take 256 microseconds to get an interrupt. So to get 100 interrupts, we must start somewhere, not start at 0. We must start somewhere so that the time it will take from that point all the way here will be 100 microseconds. Meaning it will be 100 counts. So the offset that we have to calculate, the value that we need to put here is actually your offset. The offset value is actually equals to the maximum count minus the required number of counts. So that will be 256 minus 100, and then that will give you 156 counts. So we need to load timer 0 so that every time, after every interrupt, it doesn't start again from 0, but it starts from 156. So with that said, we need to go and load here 156 every time. After every interrupt, we load 156 so that we always start at 156. That's what we need to do. Let's go and see how we do that in the program. I'm just going to say now, trying to implement this solution, I'm going to start a whole new program with the whole of this. And then later on show you how we can use this program and connect it to what we already have. Like I said, these can start off as individual programs and then you can later combine them to achieve the whole goal. So let me try and do that, but I'm not going to start a new file. Just going to do on this very same file. I will assume that this is the end of the program. I'm starting a new file. A new file still will have the same thing. List. Okay, maybe I should just do a new file before I confuse you. Let me just do a new file and then set this font. I think I did that. Still going to be the same thing because these are the same all the time, right? On the new file, I'm going to have that. This is a new file. I want to save it as let me go to documents and test program. Under here, let me go see, this is _7 segment.asm. Now, this is the 7 segment part. I now need to implement what I've just did, where I know the offset for timer 0 is 150, and then using a prescaler of 1:1, that will give me 100 microseconds. I need to enable timer 0 interrupts. I need to enable timer 0 interrupts. With the calculations, I can get 100 microseconds, and then I need to have an endless loop. Also here, because I've enabled timer 0 interrupts, while I'm in the endless loop, when timer 0 interrupt takes place, I need to come here, check which 7 segment is enabled, and if RA6 is enabled, disable it, display data for the second one, enable the second one, do this, go back to the main program. After 100 milliseconds, come here. This was now disabled. Come here, disable RA7, display data for the first 7 segment, enable RA6, come here, return from interrupt, go back to the main loop. Another interrupt, 100 microseconds, come here, do this. So it's going to change between these at 100 microseconds interval as per our calculations. Then the only thing I didn't put in here is the lookup table. Remember, to display the data, we need to have the lookup table. That I'm just going to put in as part of the display data section, right? We need 2 registers. The one that's gonna have a value to display for the first 7 segment, and another register to display for the second 7 segment. We're gonna do that in the program. Let's see. Now, at initialize, says here go to initialize, whole new program. At initialize, it says here port B must be an output. Port B outputs RA6 and RA7 outputs, and we configure timer 0 interrupts. Right. So we go to bank 1 because the trees A and trees B are in bank 1, right? So bit clear file status RP1, bit set file status RP0. We are now in bank 1. We need to make port B outputs clear file. It's B. B6 and B7 must be inputs. The rest of the other ones I'm not using. I can make them all outputs. Press A. And now configure our timer 0 so that the prescaler is 1:1. That's most important because that's what we got in the calculation. With a prescaler of 1:1, your time per count becomes 100 microseconds. The time per count becomes 1 microsecond. And now we need 100 of those counts. If a single count takes 1 microsecond, 100 of those counts gives us 100 microseconds. Because this counts from 0 to 255, giving 256 counts. To get 100 out of 256 counts, we say 256 minus the required number of counts. It gives us a point when we need to start so that when we overflow, this will be exactly 100 counts. These 100 counts resulting in 100 microseconds because each count is 1 microsecond, 100 microsecond delay. This is the value that's going to be in the timer 0 register. Timer 0 register has to start from 156 so that when it gets to 255 and goes to 256, that will be exactly 100 counts and it overflows, generating an interrupt. We need to access the option register so that we can set prescaler and configure our timer 0. Option register, 8-bit register, like all other registers. Most importantly, in terms of timer 0, we need to look at bit 5 all the way to bit 0. Right. We are going to use the timer in timer mode, meaning we're going to use internal instruction cycle, where the clock source is not from an external RA4, but the clock source is from internal instruction cycle. So bit 5 must be 0. Bit 6 is only relevant if you're using an external clock. So whether you set it or clear it, doesn't matter. I'm going to make it 0 still. Bit 3. Okay, bit 4 is the one that is relevant to whether on a rising edge or falling edge, if you're using an external clock. Bit 3 is for assigning prescaler. Are we assigning prescaler to watchdog timer or are we assigning prescaler to timer 0? This decision is based on which prescaler is available in which rate. Our calculation shows that we need a prescaler of 1:1. 1:1 is only available in watchdog timer rate. It's not available in timer 0 rate. So we're going to say bit 3, assign the prescaler to watchdog timer. Bit 3 is going to be set. And to set a prescaler of 1:1, bit 0 to bit 2, those 3 bits must be 0, 0, 0. Choosing this section and assigning prescaler to watchdog timer selects the 1:1. That is the first step, option register. Our option register, in terms of the PIC microcontroller, or this particular microcontroller, we then go back again to the memory organization. Option register is in bank 1. Option register is in bank 1. Timer 0 is in bank 0. Let's set up first the option register to set up the prescaler and everything. This is in bank 1. So we go into our program and see, while in bank 1, there's a value that we must move into option register. In binary, let's look at the option register once again. Now, this option register, bit 7, is port B pull-ups. Do we want to enable port B pull-ups? No. If you don't want to enable them, you can set this bit high. If you want to enable pull-ups, you can set them low, right? In this case, or in our application, I have connected an external pull-up on RB0, right? If I didn't want the external pull-up, I will just disconnect the external pull-up on RB0 in the circuit, and then just have here, I will have just disconnected this part, get rid of this, and just have a switch to ground, just a switch to ground. Because all port B pins have internal pull-ups. If a pin is configured as an input and you enable the internal pull-ups, this pin will internally be pulled high to VCC through an internal pull-up resistor. Then you don't need an external one. In this case, I have an external one. I can remove this external one and then enable internal pull-ups. But I don't want to enable internal pull-ups. If I want to, I will just have to remove the external one. So because I have already an internal pull-up, I will disable internal pull-ups here. Bit 7 is 1. Bit 6, interrupt edge select. I haven't actually reached to the port B interrupts here, so it doesn't really matter. I will choose when it gets there. Whether I choose rising edge or falling edge, it doesn't really matter. Let me choose the falling edge, make this bit 0. So I have 1, 0. Bit 5, I use internal, so it's going to be 0. 1, 0, 0. Bit 4, it doesn't really matter because I'm using internal, so this is going to be 1, 0, 0, 0. The first 4 bits will be 1, 0, 0, 0, right? Now, bit 3, I want to assign the prescaler to watchdog timer so that I can choose a 1:1 rate. So bit 3 becomes 1, and the next bit 3 bits becomes 0. So I have 1, 0, 0, 0 as well. 1, 0, 0, 0. This is the value that has to go into the option register. Move W to file, option register. Right. I have successfully assigned my timer 0 to run so that a single increment is equals to 1 microsecond. Now, let's go back to the flowchart and see what is that I still need to do. I've made port B outputs, I've made port A outputs, I've configured my timer to run at 1 microsecond per count. I need to go and enable timer 0 interrupts. Right. Remember, I still haven't loaded the offset. I still haven't loaded the offset, but I can enable interrupts and then load the offset later on. Let's see now. To enable timer 0 interrupts, we look at the incon register. To enable timer 0 interrupts, we look at the incon register, interrupt control register. The incon register says bit 7 is the global interrupt enabled. For any interrupt to work, this bit 7 must be set, right? So we need to enable the global, the GIE bit. So this bit becomes 1. Bit 6 is the peripheral interrupt enabled. At the moment, I'm not using any peripheral interrupts, so I disable bit 6. So this becomes 1, 0. And bit 5, the timer 0 interrupt enabled bit. This is what I'm interested in. I need to enable timer 0 interrupt. So this becomes 1, 0, 1 to enable timer 0 interrupts. At the moment, for this particular program, I'm not using RB0 interrupts. I'm going to disable them. I'm not using port B interrupts. I'm going to disable them. The interrupt flags are to indicate that an interrupt took place. And at the moment, at the beginning, no interrupt has taken place. All the flags are 0. So the number I have to put into the incon is 1, 0, 1, 0, and 3 and 4 zeros downwards. So, but now incon, let's look at the incon first. The incon register is found in all the banks. Bank 0, bank 1, bank 2, bank 3. You can move that number into incon while you are in any of the banks. It's not going to make any difference. But because in my case, I still need to go and access timer 0 and move the offset there. I will rather go switch to bank 0, where I can access both timer 0 and the incon register. So I'll say here, bit clear file, status, comma, RP0. This takes me to bank 0. Now I can say move a literal value for the incon. Remember the value will be PIE must be 1, the peripheral interrupt enable 0, timer 0 enable 1, RB0 interrupt 0, port B on change interrupt 0, and all the 3 interrupt flags are zeros. This is the value I need to move into the int on register. Here I have enabled timer 0 register, timer 0 interrupt. Enable timer 0, only timer 0 interrupt. Now I need to move the offset value. Move a literal value into W. The offset value we calculated in decimal is 156. A dot in front will mean the value that you move there is in decimal. If you're using decimal, the maximum number you can move is 255. There's no way you say move a literal value 356. It doesn't work for the 8-bit microcontroller, right? The maximum value you can use in that number system is 255 in decimal number system. Now move 156 into W, move W to 5, timer 0 register. The register that holds the timer count. I want it to start at 156 with my timer 0 interrupt enabled. After that, what is it that we do? Endless loop. We are already in bank 0, so I can have my main go to main. When timer 0 interrupt takes place, what happens? The PIC is going to jump to what we call the interrupt service routine. Interrupt service routine, which is origin 0x04. Then at origin 0x04, we can have what we call the interrupt service routine. Okay, I can say go to interrupt service routine. Now I can put my ISR there. Now, coming back to why did I have go to initialize here? Because I didn't have anything. Remember, I didn't have anything here, and I had to go to initialize. I knew that if we use interrupts, we're going to have a code between initialize and the reset vector itself, where we need to now have the origin 04 for the reset vector. So at the beginning, when you switch on power, after any reset, the program is going to start at 00, and then it's going to jump the whole thing I'm going to put here, jump directly to initialize and execute all the way down. Jump in this section where the interrupt service routine is going to be. Right. Now, when I get an interrupt at interrupt vector, what do? I jump to interrupt service routine. I don't have to jump. I can just have my ISR directly under origin 04. Origin 04, I have an interrupt. I know there's only one interrupt I'm using in this case, is timer 0 interrupt. When timer 0 interrupt takes place, what is it that we must do? Check which pin, or check RA6 if it's on or not. Right. So I'm going to say bit test file, skip if set or skip if cleared. So let's see now, according to the flowchart, if I say skip if set, it means I'm going to come to this site when it skips. When it doesn't skip, I go to that site. Sorry about that. When I use skip if set, it means when I skip, I'm going to come to this site. And when I don't skip, or if I don't skip, I'm going to come to this site. So let's use skip if set. It's fine. Bit test file skip if set. Port A, RA6. Remember, I'm in bank 0 when I did my main loop. I'm in bank 0. and port A is in bank 0. So the interrupt takes place while I'm in bank 0. I already know that I can access port A because I'm in bank 0, right? Now, bit test file skip if set port A, RA6. If RA6 is not set, go to I will say enable. So let's look at this. If RA6 is not set, then we're going to come to this direction. What are we going to do? We're going to enable the first 7 segment in this. So if it's not set, come and enable the first 7 segment. Go to enable, I will say 1 for the first 7 segment. Right. Else, if it is set, then we go to the other side. Remember, the skip if set skips only one instruction. So if it is set, we skip and we continue executing the program. In this case, we are going to enable the second 7 segment. Right. So if we skip, then it means we are going to enable the second one. I can have a label here. I don't need it, but I can have an indicate that here I'm enabling the second 7 segment. On enabling the second 7 segment, remember now, this is what has to happen. Disable RA6 because it was found to be set. Clear it, get data for the second 7 segment, and then enable the second 7 segment. Let's clear and get data. Get data, we need now to have our lookup table set up, right? So let's see how we can achieve that. Go back to the program. Here we need to disable the first 7 segment. Bit clear file because it was set port A, RA6. We need to fetch a value that will display on the 7 segment the value for the first, the value for actually the second 7 segment. We're gonna need to make use of registers. I'm gonna say hence for a general purpose register. Remember they start at address 20, right? Our general purpose register, they start at general purpose in bank 0. General purpose register, they start at file register 20 there. So temp is a name to my general purpose register at file address 20. And units is a name to my general purpose register at file address 21. Right. So on the first 7 segment, I'm going to display tens. On the second 7 segment, I'm going to display units. So on the second 7 segment, I need to fetch a value for the units, right? So I need to say move file units into W. Units will hold a value between 0 and 9 because I'm displaying decimal values on the 7 segment. And then that value, I don't know what it is. I'm going to call a lookup table. Lookup table. A lookup table has to go and fetch a value which, when I move it to port B, must display the number which is in units. Any number between 0 and 9. The number that is in units must be displayed on the 7 segment after I fetched a value from lookup table and move it to port B. Now, I've just moved the data to port B. I haven't enabled the second 7 segment. This is where I will enable the second 7 segment. Bit set file port A, RA7. Here I'm enabling the second 7 segment. Right, now I need to go put into the lookup table, get data for the 7 segment, second 7 segment, and then enable the 7 segment, then go to interrupt return, where you first have to clear the interrupt flag and then return from interrupt. So Now I can say here, if my return from interrupt is a label, I will say go to interrupt return. I'll just call it interrupt return, abbreviate it like that, and have that label somewhere there. And at interrupt return, what is that I must do? At interrupt return, I must first clear the timer 0 interrupt flag and then return from interrupt. The timer 0 interrupt flag is incon bit 1, which is int. Okay, no, it is incon bit 2, which is timer 0 if. Incon bit 2, which is timer 0 if. I can use the name instead of the bit number. So I'm gonna say bit clear file. The file is incon register. The bit is timer 0 interrupt flag. And then the last thing to do is return from interrupt. Return from interrupt is a special type of a return written like that. So that will be return from interrupt. I've managed to do this part of the program. I've done this part of the program. I haven't done this part. I need to now go do this part. Where is this part? In our program, that is when we didn't skip. So I said here, bit test file, skip if set RA6. If it is not set, go to enable the first 7 segment. Then I copy that label, put it just under enable 2, put enable 1 there, and at enable 1, still the same thing applies. I need to disable RA7, get data for the first 7 segment, and then enable RA6. The process will be exactly the same as this one, except that I will change few things. So I'm going to copy this code, paste it there. Disable the bit clear file. This is going to be RA7 instead of RA6. Now the data for the first 7 segment is in tens, not units. So I'm going to take tens. For the first 7 segment, the data is tens, not units. Get the value from the lookup table, move that to port B, and enable the first 7 segment, not the second one. So the first is enabled by A6. This will be the first 7 segment. Right. Now, the only thing left here is to define what lookup table is. So lookup table, I will have it there. And then because I have it here, that won't disturb my ISR, because I'm saying origin 0, when I get an interrupt, jump to ISR. It's going to jump and skip the whole lookup table program. That's the one thing powerful about GoTo. You need to know how it works and how to use it. Besides that, the program I said is going to be executed sequentially from top to bottom. Pay attention to your GoTo, your call instructions, how you use it. Lookup table, add W to file is always the first instruction. PCL, comma, 5. And then you have a bunch of returns there. Return literal with W, a value that will display 0, 1, 2, 3 up until 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Those values, I've already calculated them, or I've already defined them in the 7 segment display with lookup table video. In this case, I just need to consult part of that. To display 0, I need to return with 7E. So the values are going to be 7E, 0C, B6. OX7E, OX0C, OXB6 for the first 3. And then the others, the 9ECCDA. 9ECCDA. And then the next three will be FA0E, FECE. FA0E, so let me just verify the last two. There will be FECE. All right, is all correct? Perfect. That is my lookup table. Now, this is the 7-segment multiplexing program. I'm gonna try build this program and see if it's going to do that. All assembly language or assembly programs that you write in this platform, they always have to end with the end instruction there to indicate the end of the program. We start to see if I can quickly build this without problems. Once that is done, I want to see if I can simulate this program and get it to work. I'm not going to use PC serial. The microcontroller I'm using is the PIC 16F8. That's my microcontroller there. On default, analogs are enabled, so those pins, that's what I was talking about. You need to disable analogs at the beginning. And let me load the program. Let's see now. I need the 2 7 segments. So where are the 2 7 segments? 2 7 segments, I need to enable them. One on enabled by RA6, the other one enabled by RA7. Right. Let's see if this program, you see it's displaying 0, 0. On the simulator, it will be as if only 1 7 segment is displaying at a time, because this is it is not running fast enough. In actual time, that hasn't even made 1 second. This will be the actual time when you look at real-time duration. But switching between the two so fast will seem as if they are all on at the same time. Because I'm displaying 0, 0 on both of them, the data on port B is not changing. What is changing is which 7 segment is enabled at a time. To display different values, after I initialize this, I can load initial values. So say, move a value into W. Let's say I want to display 25. I will say move a value between 0 and 9. 2 in this case, move it to file the tens, and move a value 5 in this case, move it to units. If I build this program and then update my microcontroller with the new program, start simulation, this will be 2.5. It will be 2.5. On the simulation, it might not seem as if it's a constant 2.5. In actual hardware, it will be 2.5. What's important is that 2 is on the first 7 segment, 5 is on the second 7 segment. You will never see 2 here. If you see 2 moving from the first to the, then it means there's something wrong with your multiplexing. Right. So we have achieved 7 segment multiplexing. We now need to merge the 2 programs. I don't want to have too many programs and merge them later on. I want to merge this program with the one we did where we enabled few things. So we now need to merge these two programs. Remember, our goal is still that big problem that we need to achieve at the end of the day. But now we're going to do it piece by piece. Piece by piece. This is going to be a very long video, right? Now, the easy way is, this is already a long program and this is a small program. I can easily take whatever is in here and put it there. I need to check the similarities. Go back to the flowchart. Check the similarities. In here, do I have anything that is repeating on this side? Because I want to take this program, put it here instead of taking this one to that side. I want to take this one, put it on this side. This and this are the same. So I don't need this. It's already there. Right? And now, go to initialize is there, initialize. But is there a point where I'm setting oscillator to 4 megahertz? It isn't there. So I just need to take this part to the 4 megahertz part. Let's start with that. 4 megahertz part, I'm doing it in bank 1. And this is the part I'm doing there for 4 megahertz, setting the internal oscillator to 4 megahertz. I'm going to take this part, cut it, and put it. But I must paste it in this program where I'm in bank 1. Right, so I'm going to go back to this program of the 7 segment where I am initializing and say, while I'm in bank 1, it doesn't matter whether before clearing the trees or what, or after, I can put that there. And then here I'm configuring my oscillator, internal oscillator. For 4 megahertz. Right? Now, after that, I still need to do something. Looking at the two flowcharts, I'm done with the 4 megahertz oscillator. The watchdog time, period. 2.097 seconds. I need to take that part and move it here. And that happens, remember now, in bank 2. To do this, to set up this time, I had to go to bank 2. In this program, there's no point where I went to bank 2. Right? There's no point where I went to bank 2. I went to bank 1, set up the outputs. I just inserted the program where I set up the oscillator. This was already part of the 7 segment program where I'm setting the prescaler and timer 0. This all happens in bank 1. I can put this one anyway because it's already in bank 1 and everything is in bank 1. But the watchdog time happens in bank 2. I must be careful when I put it that it must be in bank 2. I'm going to switch to bank 2 by setting RP6, clearing RP0, and then take the whole of that. Because there's no point where I'm switching to bank 2 in the 7 segment program. I have to switch to bank 2 so that I can set that up. So I'm going to come here and see. Let's go and put this. Where do I put it? Do I start with bank 2 first? I can start with bank 2 first if I want. It doesn't really matter. We can put it under bank 1 or under bank 0. As long as at the end of the day, when you execute your main program, you're in a correct bank. I want to end up in bank 0 where I'm executing everything while I'm in bank 0. So let me rather start by bank 2. So I start by going to bank 2, configure my watchdog timer, and then go to bank 1, configure everything that happens in bank 1. I can put this also before everything else, and then still continue with this A and this B after that. And this will be more or less the 2nd or the 7 segment program, where from the top here it's part of the oscillator setup program, right? But the most important thing is you don't want to repeat things and you don't want to do things in the wrong bank, right? So as far as it stands, I've managed to take this and put it there. I'm done with this part. In this program, there's just one thing that we didn't do. Because we just enabled a watchdog timer, we now need to be careful that watchdog timer mustn't reset our microcontroller. Because if I don't clear it within 2 seconds, 2.9 is always going to reset. Meaning, as this program stands, watchdog timer is always going to reset our microcontroller every 2 seconds if we run it. But now this microcontroller, because it's running one function, one program, we might not be able to see that. If I just run it as it is, it's always going to run resetting every 2.07 microseconds. If there was a way for you to see it, you could, but because if it resets, it's still going to do the same program. It doesn't really matter. Now, watchdog time, we set the period to 2.097 seconds. We need to clear the watchdog timer before that period expires. To clear a watchdog timer in this application is very easy. In my main loop, I'm just going to have an instruction that clears the watchdog timer. An instruction that clears watchdog timer. Which one is that? Let's go back to our instructions. If it's here, I don't know. I don't think it's here. Okay, the clear watchdog timer instruction is not part of these instructions. Oh, it is. Oh, yes. Clear watchdog timer. That is the instruction. Clear watchdog timer. That's the instruction that I need to put in there. So I'm going to say here, clear watchdog timer. That is my instruction. So this instruction, I'm always going to execute it because it's part of the loop. Meaning the watchdog timer will never get to exceed 2 seconds without being cleared. This system will never reset. The purpose of watchdog timer. Let's say, for an instance, at some point, you get an interrupt, the PIC jumps to the interrupt service routine, and it gets stuck here. Right? If it gets stuck in the interrupt service routine, it will never return. And if it takes more than 2.9 seconds stuck in the interrupt service routine, the whole system is going to reset due to the watchdog timer, because this instruction can only be executed once the PIC has returned from the interrupt. So you get an interrupt, it leaves the main program, goes to service the interrupt, and if it gets stuck somewhere in the interrupt, after 2.097 seconds, it's going to reset and start all over again. This prevents a system from being stuck forever. Right, the watchdog timer prevents a system from being stuck forever. So now we have achieved a number of things this far. As far as this thing is concerned, we managed to get to creating lookup tables. Let's now create a timer interrupt where we'll get a 1 second interval for that timer interrupt. Right? I've already used timer 0 for 100 milliseconds interrupt. I can't use it for 1 second interrupt. I have to use another time. So I'm going to use timer 1 to generate a 1 second interval. Now, to do that, let's see timer 1 and how one can use timer 1. Timer 1 has a register called the T1 register, T1 con register. The T1 con register is just the timer 1 control register. It's an 8-bit register. And timer 1 is a 16-bit timer. It's not like a timer 0 where you only have 8-bit count from 0 to 255. For timer 1, we have 2 sets of registers, timer 1H and timer 1L, which gives us a 16-bit timer being able to count from 0 to FF. 0 to 65,535. Right. Timer 1 then gives us a better resolution if we want to achieve bigger delays without having multiple cycles. Right. But now, timer 1, the timer 1 prescaler can range from 1:1 to a maximum of 1:8. We don't have a higher prescaler like we do for timer 0, where you can get 1 up to 256. For timer 1, our maximum prescaler is 1:8. But we can still use 1:1 depending on what are the requirements. Calculations for timer 1 remain the same for timer 0 if we use timer 1 clock source as our internal instruction cycle. Here, timer 1 clock source can be internal instruction cycle or can be the clock from RB6. If we use internal instruction cycle, the clock rate, the run rate is still F oscillator divided by 4, as it is with timer 0, right? And then using this timer 1 control register, we can enable timer 1 there by setting bit 0, set the clock source to internal clock cycle, synchronizing it. It doesn't really matter if you're using the internal, and then oscillator, we don't need timer 1 oscillator because we're using the internal, so we can shut off that timer 1 oscillator. We set our prescaler, and then this is the status bit. We can initialize it as 0. It's just an indication of the status of the timer 1 clock. Right, bit 7 is 0. We can get a value here. Now, with that value, when we move it to timer 1, we can configure the rate at which our timer 1 runs, and then we go and set up timer 1 interrupts. Let's start with the calculations. We want to achieve a 1-second interval with our timer 1, knowing that this is a 16-bit time. Going back to these calculations, for timer 0, we had count from 0 to 255 overflowing at 256. For timer 1, we count still from 0 1, 2, and so on, but we can count up until 65,535. When it goes to 65,536, it overflows. It overflows when it changes from 65,535 to 65,536. It flows. Now, the calculations I said, they will remain the same because if we use internal clock, this would still be the running speed if we use a prescaler of 1:1. But now, our required delay has changed. Required number of counts will be equal to the required delay divided by the current time per count. Now, our required delay is 1 second. Our time per count is 1 microsecond. That gives us a count of 1 million. Yes, we need 1 million counts. But now, with a 16-bit timer, we can count up to 65,000, not 1 million. This is with a prescaler of 1:1. With timer 1, we have a prescaler of 1:1 up to a prescaler of 1:8. We now need to find out which prescaler should we use to get the count to be less than 65,536. Right. So to do that, we now need to go and calculate the minimum required prescaler. The minimum required prescaler, you can calculate it by saying the required prescaler will be equals to the required number of counts divided by the maximum possible count, in this case, which is 65,000. So the required prescaler will be the required number of counts, 1 million counts, divided by the maximum possible count we can get, 65,536. That's when it overflows. It overflows at 65,536. So when we get there, that's when it overflows. That is our maximum count. This will give us our required delay to be what? If you perform calculations for this, you will get that you have 1 million divided by 65,536. That will give you 15. It's too bad. That will give you 15, right? 15 point, where's the calculator? 15.25. So 15.25, we don't have, for timer 1, we don't have a prescaler greater than 8. Then we'll just have to stick to the prescaler of 8, right? Now, as we continue with our calculations, we then have to choose our prescaler to be, obviously now, 8, because we don't have any other option. So our prescaler that we'll choose will be 1:8. If we choose the prescaler of 1:8, time per count will change. Because now the new time per count with a prescaler of 1:8 will be equal to that 1 microsecond and multiplied by 8, which will be equals to 8 microseconds. That will be your new time per count. With 8 microseconds now, we calculate the required number of counts. Required number of counts will now be the same delay we are wishing for, 1 second divided by the time per count. The time per count is now 8 microseconds. Required number of counts will be 1 second divided by 8 microseconds. Where is negative 6? That will give us 125,000 counts. Our required number of counts is 125,000 counts to achieve a 1 second delay. But we can't get 125,000 counts still, because our maximum count is 65,536. That's the maximum we can get. So how are we going to get that 65,566? How are we going to get 125,000 out of this 65,536? It means now we don't have any other choice but to circle twice to achieve that. I'm saying circle twice because obviously 65,000 twice will be greater than 125,000. You can verify that by saying now that we know we can get 1 second within 1 cycle, how many cycles do we need? How many number of overflows do we need? The number of overflows we'll need will come from your number of overflows will be equals to the required number of counts divided by the maximum count. How many times the maximum count fits in the required number of counts? Then that will be required number of counts 125,000 divided by maximum count 65,536. And then that gives you 1 point something. Because we don't have decimal points in a PIC, that will be 2 automatically. So this divided by 65,536 will give you 1.907, which we will regard it as 2. More or less, we will equate it to 2, right? Now we need 2 revolutions, but actual 2 revolutions won't make 125,000. We'll make a little bit more than 125,000. So if we need 2 revolutions, each and every revolution, how long should each revolution take? Now, number of counts per overflow will be equals to the required number of counts divided by the number of overflows. Your required number of counts divided by number of overflows. Your required number of counts 125,000 divided by number of overflows, we calculate it to be 2, and then that actually gives us 125,000 divided by 2 gives you 62,500. 62,500 can fit within 65,536. Now, but this will be 62,500 twice to get 125,000 counts. Now, this overflows when 65,536 goes to 65,535, when 65,535 goes to 65,536, and instead going to 0. We need to calculate the offset the very same way we did with timer 0. Meaning we don't need 65,000, we need 62,500. How do we get 62,500? We need to start somewhere. We don't start at 0. We need to start somewhere with our timer so that when we get here, this will be 62,500. Right. So to get that, it is still an offset calculation to say our offset value will be equals to will be equal to 65,536 minus our required number of counts per cycle this time around, which is 62,500. And our offset, we will find it to be 65,536 minus 62,500. That gives you 3,036. That's our offset. Now, remember, we are able to count from 0 to 65,000 because in this case, timer 1, it's a 16-bit, not an 8-bit. 16-bit, we have 2 registers for the upper 8-bit and the register for the lower 8-bit. We need to get an offset where we load 3036 into the offset register. So that's basically what we have to go and do in terms of timer 1. First of all, we know that our prescaler we need to get is 1:8. Let's go and implement that in terms of timer 0, in terms of timer 1. Timer 1 control register. We need to set prescaler 1:8. We need to chart the timer 1 oscillator because we are using the internal clock cycle. This can still be 0 because it's irrelevant. We use internal, this must be 1. We want to enable timer 1. Okay, we use internal, this bit must be 0. We want to enable timer 1, so this bit must be 1. We're going to do that in the program. But now, timer 1 control register, in which bank is it? In which bank is it? T1 con is in bank 0. So we have to do this when we're in bank 0. I'm just going to do this in the current program we have because it's not that much. Once we go into bank 0, the first thing I want to do is set up my timer, move electoral value into W. In binary, let's look at all the bits. Bit 7 is 0. Bit 6 is a status bit. We are not deriving the system clock from the timer 1 oscillator, but from another source. So I'm going to make bit 6 0. So 7 is 0, 6 is 0, 5 and 4 are 1 1. So this is 0 0 1 1, the first 4 bits. Move a value 0 0 1 1, and then the last 4 bits will be sorry about that. Bit 3, timer 1 oscillator, we are not using it, so we shut it off. Bit 3 becomes 0. Bit 2 becomes irrelevant because we are using internal clock. So this becomes 0 0. Bit 1, we want to use internal. This becomes 0. So we have 0 0 0, and we have 1 for bit 0. 0 0 0 1. In bank 0, this is the value that must go into timer 1 control register. Right. I've just initialized and set up timer 1 to run at a prescaler of 8, 1:8. Timer 1 on 1:8 prescaler and running from internal clock cycle. Right. Now, I still have to load the offset. I still have to enable timer 0 interrupts. Now, let's start with loading offset. After here, I was loading actually a timer 0 offset. Let me load timer 1 offset. Let me load timer 1 offset. To load timer 1 offset, I need to load now 3036. I need to load 3036. I can just go here and say, in programming mode, decimal number 3036. In hexadecimal will be BDC, 0BDC. Because timer 1 has 2 registers. The upper register will have 0B, the lower register will have DC as my offset. Now, whenever you are writing to timer 1 registers, the count registers, you always have to write the timer 1H and the timer 1L. You always have to write to the timer 1H first before you write to the timer 1L. Or what you can do is you can clear timer 1L, write to timer 1H, then write to timer 1L. The reason is you don't want timer 1L to overflow and increment timer 1H while you were busy writing timer 1H. Right. Because as it counts, it increments the lower bits. When this gets to 255, it increments that, starts all over again. Increments that, start all over again. So while you are busy writing here, it might change the value when it overflows. You can start by clearing timer 1L, write timer to timer 1H, and then later on write to timer 1F. Right? Because once you clear it, it's going to start from 0, giving you time to write to timer 1H. Timer 1H and timer 1L are just registers which will hold your value that will range from 0 to FFFF, which is 0 to 65,535. Now, timer 1H and timer 1L, in which bank are they? They are still in bank 0. Timer 1L, timer 1H. They're in bank 0. I don't have to switch the banks. I can just directly go and write the clear first, clear file, timer 1L, so that it doesn't overflow and change the value of timer 1H. We want to move into timer 1H. The value we got here, remember we need to load offset of 3036. 0B on timer 1H, DC on timer 1L. Move electrical value into W, OX 0B. Move W to file, TM1H. And now we can move literal to W. Move literal to W. OX, is it DC? Yes, DC. Move W to file, TMR1H. No, TMR1L this time around, right? So the H is there, the L is there. We've loaded our offset. But unlike the timer 0 calculations, the timer 1 calculation, we found that we need 2 cycles to achieve 1 second. Whereas in the timer 0 calculations, we just needed 1 cycle to get 100 microseconds. For the timer 1, getting a 1 second, we need 2 revolutions. So we need to count the number of revolutions. We need to have an extra register that will count the number of revolutions. So we load our offset. I can also load 2 to indicate that we need to start from 2 revolutions. Move a literal value in decimal 2. You can do it in hex. Move W to file. I can name this file anything. I will just have to declare it also as a general purpose register. You can name it maybe as count, right? So we need to make sure that we are counting number of cycles. So count will be a general purpose register at the next available address, which is memory address 22. Equate address 22. Now, initially, count will have 2 in it. We need to start from 2. When it gets to 0, then we know it is 2 revolutions, right? We haven't enabled timer 0 interrupts. So timer 0 will run, but no interrupts will take place yet. We need to go and enable timer 0 interrupts. No, sorry, timer 1 interrupts. We haven't enabled timer 1 interrupts. Timer 1 will run, but it will not cause any interrupt. To go and enable timer 1 interrupt, we now look at where do we find timer 1 interrupt. Looking at the peripheral interrupt enable register 1. We have bit 0 there to enable timer 1 interrupt. We want to enable timer 1 interrupt, we need to access peripheral interrupt enable register 1, and then bit 1 enables timer 1 interrupt. The next one is for timer 2 interrupt, capture compare interrupt, synchronous serial port interrupt, UART transmit, UART receive, and ADC interrupt. We are not interested in any of these interrupt except for timer 1 interrupt. So only bit 1 must be enabled, the rest must be cleared on PIE 1. But PIE 1, it is just the peripheral interrupt enable. For any peripheral interrupt to work, bit 6, peripheral interrupt enable bit. This bit 6 together with bit 7 of the int con must be set for any interrupt in this peripheral to work. For any of these interrupt to work, bit 6 of the int con must be enabled because it makes way for all of these to work. Right. So we're gonna need to revisit incon register, ensure that bit 6 of incon register is set, and then we come to PIE, we set only bit 1, bit 0 actually, bit 0 of the PIE 1 register. Now this is the enable bit for the timer 1 interrupt. The next register there is the peripheral interrupt request register. Bit 0 of that register indicates if timer 1 interrupt took place or not. Remember, the flag is an indicator, and then the flag must always be cleared in software after the interrupt has taken place. We need to also access this after the interrupt has taken place so that we can clear this interrupt flag. The PIR1 is where the flag is. The PIE1, that's where we enable the interrupt. So we need to access PIE, set bit 0 of PIE. PIE is in which bank? PIE is in bank 1. PIR is in bank 0. The interrupt flags are in bank 0. Interrupt enable are in bank 1. So in bank 1, we only need to set bit 0 of this register. This is very simple. We go to the program. Whenever, everywhere where we in bank 1, we can add an instruction, move literal to W. Now this one is very easy. OX01. I don't even have to do it in binary. Move W to file PIE. Here I'm enabling timer 1 interrupts. Enable timer 1 interrupts. Now the flag on default is cleared, so I'm not going to clear it. I'm just going to clear it when the interrupt takes place. I've enabled timer 1 interrupts here, but remember I still have to go visit incon, set bit 6 of the incon. Bit 7 is set already. I need to set bit 6 so that peripheral interrupts can also take place. That becomes 1 right there. And then the timer 1 interrupt will then take place. Now, when the timer 1 interrupt takes place, we are always going to jump to what we call the interrupt service routine. So origin 04, go to ISR. At ISR, here I'm executing instructions for timer 0 interrupt. But this time around, I have both timer 0 and timer 1 interrupt. I need to identify which one took place and which code to execute, the timer 1 interrupt code or the timer 0 interrupt code. Then before I execute any code, I need to identify which interrupt took place. I can do that by using interrupt flag, because when the interrupt takes place, the corresponding flag is set. So if I want to execute the timer 0 interrupt, I can test maybe the timer 0 flag. Bit test file, skip if this bit is set. Which bit? Timer 0 flag is in the incon register. So if we go to the incon register, timer 0 flag is there, and it will be set when the timer 0 interrupt takes place. I just need to come here and check if this bit is set. So I say bit test file skip save incon, comma, timer 0 interrupt flag. If that bit is set, then I know timer 0 interrupt took place. Then it means I'm going to skip the next instruction that's going to come here. I'm going to execute timer 0 interrupt. So here I'm going to have, I know whatever here is timer 0 interrupt that took place. Else, it was not timer 0 interrupt. If I don't skip, it means this bit is not set. The interrupt that took place was not timer 0 interrupt. I only enabled 2 interrupts here. So if it's not timer 0, obviously it's going to be timer 1 interrupt. Then I need to go and define what must be done in timer 1 interrupt. Once I get timer 1 interrupt, I'm going to have there. And then this is my 1 second interval. No, it's not 1 second interval yet, remember, because I need to count. Sorry. I need to count how many times does this interrupt take place. It has to take place 2 times. It has to take place 2 times so that it makes 1 second. And every time it takes place, I need to reload the offset. So whenever that interrupt takes place, I need to reload the offset. So I'm going to copy this code, put it here, and then after loading the reset, I need to check, is it for the second time? Decrement file, skip if the results, after the decrement, skip if the results are zero. What is the file? Count. Save the decremented value into count. Now, remember we loaded 2 into count initially. 2 into count, we want to count number of revolutions. The first time we decrement count, the results is going to be 2 minus 1 becomes 1. The results are not 0, you're not going to skip. If you're not going to skip, we want to return from interrupt. But we can't return from timer 1 interrupt without clearing the interrupt flag. So we either clear it before we return, or we have to clear it immediately when we get into the interrupt, into the timer 1 interrupt. So I can say bit clear file, the timer 1 interrupt is in the PIR1 register, and it is bit 0. So I want to use the name of the bit instead of the bit number. We go to PIE1, we have PIR1, that is timer 1 enable, timer 1 interrupt flag. Bit clear file PIR1, which is in bank 0 as we saw, it's in bank 0 PIR1. So the interrupt takes place while I'm in bank 0. I don't have to worry. Bit clear file PIR1, the interrupt flag is timer 1 interrupt flag. Now, after clearing the flag, I load the offset. Check if this is the second interrupt. If it is not the second interrupt, just return from interrupt. If it is the second interrupt, then it means this is the 1 second interrupt. This is the 1 second interval. I want to load 2 again, so that to get another 1 second, I need to have 2 revolutions. So move 2 into W, move W into count. And then whatever you do here will be whatever you have to do for the 1 second interval up before you return from interrupt. So you will add the code here. The code that must take place every 1 second, you will add it here, and then you will later on return from interrupt. Then here we have cases, we have a case where we have both timer 0 and timer 1 interrupts enabled, and we can identify which one took place and execute the code for that one interrupt that took place, right? And we have a watchdog timer enabled, clearing it in the main program, so that if the program gets stuck in one of the interrupts, whether timer 1 or timer 0, if the program gets stuck in there and it never returns, the watchdog timer will reset the system. So far, what have we achieved in terms of what was asked of us? It's going to be a very long one. We managed now to generate a 1 second interval and integrate this in the 7 segment program. We now need to go and do the ADC program. We still have to do the ADC program, and then we write the EEPROM program, and then we check the temperature if it is above and below. If we can do these 3, we will have achieved what was asked entirely. Right, so let's try and continue. Now we are going to do the ADC part. The ADC part, we are going to use RA0 as an analog input, set our VDD and VSS as analog references, and perform ADC to get ADC results, convert those results into temperature, and in this case, because we want to display this temperature in the 2 7 segments, and because we already have registers, tens and units to display on the 27 segments. We're going to put the results in tens and units, and then the multiplexing will just display those results for us. We just need to acquire ADC, convert the results into temperature, and then put the temperature into tens and units. The multiplexing will take care of displaying that for us. And because we have to perform ADC every second, the ADC program is going to come here. I hope you see where we are going. The ADC program is going to come here. But let's write an ADC program alone first. So let's write an ADC program alone. So we're going to write our ADC program. Go to initialize. To perform ADC, we still need to get a flowchart for our ADC. Right, so this one is done. We are happy with it. We even added timer 1 interrupt, although I didn't make lookup table for timer 1. I didn't make the flowchart for timer 1, but we have already added it there. Start still will be there. ADC, right? Initialize will be there. Start. At initialize, we need to set up RA0 as an analog. As our analog input, and VDD and VSS as our analog references. After setting up these few things, even there might be other things that we want to do. We may want to do. We then go into the main program where we will perform ADC on our A0. Okay, perform ADC on RA0 channel, and then get the results. Convert those results to temperature. Convert the results to temperature. And then move them to tens and units for display. That's it. We set up our ADC. From the beginning, we're going to go configure certain things, our pins as RA0 as analog input, set up our ADC references. Then later on, go and perform ADC on RA0, convert the ADC results we get, convert them to temperature, 2-digit temperature reading, move those results to tens and units for the 7-segment multiplexing to display those results. That's it. Right. This might not be as easy as it sounds, but it's possible. So let's go and do it. ADC. First of all, we want the RA0 pin to be our ADC. We need to go and look at ADC part of the datasheet. Remember, ADC or datasheet is a referral manual. You can jump to the section which you are interested in so that you can quickly configure it and make use of it without having to read from the first page to the last page. Now, if we go to the ADC, one of the registers we need to look at is the ANSEL register. Remember I said the pins on default, they come as analog inputs, and you set them as either analog or digital using the ANSEL register. So it says here, the ANSEL register. If the ANSEL bit is set, that pin becomes an analog input pin. If the ANSEL bit is cleared, that pin becomes a digital pin. And then the ANSEL register, it has 8 bits, but bit 7 is unused, always 0. And then we have ANSEL 0, ANSEL 1 up to ANSEL 6. This will be analog channel 0, which is on A0, A1, A2, A3, A4, B6, and B7. So we want only this pin to be analog, meaning only bit 0 of ANSEL to be set, the rest to be digital. So only bit 0 of ANSEL should be set. That's one thing. But let's start a program by saying origin 00. These are overheads that must always be there. Origin 00, go to initialize. At initialize, we need to go and access ANSEL. ANSEL is in bank 1. So we need to switch to bank 1. At initialize, we switch to bank 1 here. Now we need to set only bit 0 of ANSEL. Move electoral value into W, 0x01. Move W to file, ANSEL. Right. We have managed to make only RA0 as an analog input pin. Right, we still need to set up a few things when it comes to ADC. We still need to ensure that we have VDD and VSS as our analog references. To do that, we continue now to the next ADC register. I think that register will be the ADCON1 register. The ADCON1 register can configure certain pins, either external pins or VSS and VDD as our references. We don't want to use external positive and negative references. We want to use VDD as our positive reference, VSS as our negative reference. So bit 5 and bit 4 must be 0 to do or to configure VDD and VSS as our references for ADC. Bit 0 to bit 3 of this register are unused, always 0. Bit 4 to bit 5, we want them to be 0, 0 so that a positive reference is VDD, negative reference is VSS. Pin 6 has to do with the clock divide for the ADC clock. We don't want to divide. I don't want you to stress about timing calculations for ADC. So let's just disable that. So all these bits are zeros, even bit 6 is 0. Bit 7, very important. Our ADC results, are they right justified or left justified? We need to go and find out what is it that we prefer. What does left justified mean? What does right justified mean? Your ADC results are a 10-bit ADC value that can be found in 2 registers, address H and address N. Now the 2 registers, they make a pair which makes 10 bits, right? So if your results are right justified, if you make your results right justified, the lower 8 bits of your ADC will be in address L, and the 2 upper bits will be in address H, making 10-bit value. The 2 upper bits will be in address H. The 8 lower bits will be an address L, making it a 10-bit value if it is right justified. If it is left justified, the 8 most significant bits will be in address H. The 2 least significant will be in address L, bit 6, 7, the upper 2 bits in this case. The upper 2 bits of address L and the 8 bits of address H if you're using left justified. In this application, I want to use right justified, meaning I want to set, or I have to set bit 7 of ADCON1. To get right justified, I want to set bit 7. I'm not willing to divide the clock, so this is going to be 0. The rest of the bits are 0. So only bit 7 is set on ADCON1, and ADCON1 is in bank. In which bank is ADCON1? ADCON1 is in bank 1. So while I'm in bank 1, in my program, move a literal value into W. The value is 80 in hexadecimal. Move W to file ADCON1. Right. I've managed to successfully set my voltage references and set my results whether right justified or left justified. What else do I still have to configure in terms of ADC? Is the ADCON 0 register. ADCON 0 register is in bank 0. What does ADCON 0 register do? For me to perform ADC, according to this lookup table, after setting all of these up, I need to go perform ADC on RA0. For me to perform ADC, I need to make use of the ADCON 0 register. And specifically, I want to perform ADC on RA0 channel. So on ADCON 0, let's not worry about timing calculations. So for bit 6 to bit 7, we are going to use the internal ADC clock. For how long is it going to take for the hold time for the ADC and the ADC performance? We're just going to use the internal. There's no need for us to identify what division we should use. We use dedicated internal oscillator for ADC. Bit 6 and bit 7 are set. We want to select channel 0, where RA0 is the one connected to the ADC module. So this is going to be 1, 1 for bit 6 and 7, 0, 0, 0 for bit 5, 4, 3, right? And then this value is the value that we must move into ADCON 0. ADCON 0 is in bank 0. So we need to go first to bank 0. Bit clear file, status, comma, RP0. This takes us to bank 0. Now we need to move a value now. Binary value 6 and 7 are set. 5, 4, 3 are cleared. Five, 4, 3 are cleared for selecting channel 0. And then at the moment we are just setting the ADC. We don't want to start yet. If you already want to start, you can start by setting that. At the moment, I don't want to start the conversion. So the conversion is not in progress. This bit, I'm going to make it 0. Bit 2 is going to be 0. Bit 1, I'm going to make it 0. Bit 2 and bit 1 are 0. Bit 0, I need to enable this ADC because I'm going to use it. I need to power it on. This is either powering it on or off. I need to power it on. So bit 0 is going to be 1. So I'm going to have 0, 0, 1. That's my last 3 values. And then that must be, or that must go to ADCON 0. I've set up my ADC now. I can start here to perform ADC. I can now start performing ADC on RA0. And then after performing ADC on RA0, I need to convert the results to temperature and move the value into units and tens for displaying. Right. I can do that. How do I start ADC conversion? How do I start ADC conversion? To start ADC conversion, after selecting the channel and the speed and everything and switching on the ADC module, bit 2 of the ADC con 0 is the one that you use to start or initiate ADC. You set this bit. Setting this bit starts ADC. That's what it stays there. You need to set this bit so that you can start ADC. And this bit will automatically be cleared by the microcontroller when ADC is completed. So you start this ADC and you wait until that bit is cleared. You start ADC by setting this bit and you wait for this bit to be cleared by hardware. The hardware will automatically clear this bit once ADC is completed. Meaning you set this bit, once that bit is cleared, you will know, or by that time, it will tell you that the ADC is completed and your results will be ready in the two registers, address L and address H. After ADC is completed, your results will be ready in address L and address H, depending on whether you decided left justified or right justified. In my case, I have right justified. Right. So my results will be ready in this particular manner. Now, to initiate ADC in the main program, I'll say bit set file AD con 0. The bit is bit 2. The name of that bit is go. So I can say comma 2 or comma go. Bit set file AD con 0, comma go. Now, while I wait, this is initiating ADC, right? Initiate ADC. Now I need to wait for ADC to complete. ADC will be completed when that bit is cleared. So I set that bit and I wait for it to be cleared. Bit test file, skip if this bit is cleared. Which bit? The same bit, AD con 0, comma, go. If this bit is not cleared, wait or keep on testing it. If this bit is not cleared, go to let me just say underscore wait. And where is wait? Wait will be right here. Go to wait. When I say go to wait, where does it go? It comes back here. What does it do? Test this bit again. Is this bit cleared? As long as this bit is not cleared, you wait in this routine until that bit is cleared. When that bit is cleared, it's only then you are going to skip this go to. When you skip, this ADC is complete. Then you can go and fetch your ADC results from address H and address L register. Now, your result will be in the address H and address L. Address H is in bank 0, address L is in bank 1. That will be a 10-bit result of ADC. It really means nothing, but just 10 bits. You need to quantify that data. You now need to quantify that data and say, what does it mean really? Your ADC results. In this case, we have our reference voltage as ground, which is our VSS, and our positive voltage as VDD, which is in our case, supply voltage of positive 5 volts. Now, our ADC is an 8-bit value. 0, which is our ground, is equivalent to 0 when we perform ADC. This will be analog on this side. This will be digital on this side. So 0 volts is equivalent to digital 0. 5 volts is equivalent to digital 10, 23. Because maximum value you can get from a 10-bit, it is 1023. 1023 is equivalent to 5 volts, whereas 0 is equivalent to 0 in decimal. Now, in terms of temperature, what does this mean? Remember, we are measuring the analog voltage from the temperature sensor, and we need to display that as temperature, not voltage. We want to display it as temperature. Now, where do we go? Let me see. We now have to go to the schematic and see. We have the temperature sensor giving us an analog voltage into RA0. This analog voltage is allowed to change between 0 volts and 5 volts because that is the reference. Reference is 0 volts on the ground and positive reference is 5 volts, which is VCC. The analog voltage is allowed to change between anything between 0 volts and 5 volts. But the temperature sensor gives us analog voltage equivalent to temperature. And it says 10 millivolts per degree Celsius. For each and every 10 millivolts, there's a temperature change of 1 degree. Starting from 0, one will have to go and look at the data sheet of the LM35 and get the specifications. But because already I know that, and if necessary, I can try and get the data sheet for your temperature sensor, for your LM35 temperature sensor. Let's see if I have, or I can quickly get that. LM35, do have that. This is the configuration we're going to use. Now, here it says your supply voltage, anything between 4 volts and 20 volts. You have 3 terminals on LM35, VCC, ground, and the output signal. 0 volts plus 10 millivolts per degree Celsius, meaning each and every 10 millivolts will be equivalent to 1 degree. In terms of analog voltage, back to our analog. If we have 10 millivolts there, just above 0 volts, if we have 10 millivolts, what will be the digital value equivalent to this 10 millivolts? And in temperature, we know already that will be 1 degrees Celsius. If we have 20 millivolts there, what will be the digital value? And in temperature, we know it will be 2 degrees Celsius, and so on and so on. So because in my case, I want to use a step size of 1 degree, detect 1 degree, not 0.5 degrees, not 0.01. I just want to pick up the temperature from by steps of 1 degree, 2, 3, 4, 5. I have a reason why, and you will see why. Let's just get a value that will represent 10 millivolts to start with. A digital value that will represent 10 millivolts. How are you going to get it? You will just have to perform cross multiplication. To get a digital value that will represent 10 millivolts, we'll say 1023 is actually equivalent. Let me do this in scientific. 1023 I just want to do it this way. To get that, we'll say 1023, we know that it's equivalent to 5 volts. So to get that, we'll say 1023 divided by 5, cross multiplication, and then multiply by the voltage that we want to get its digital value. Multiply whatever the voltage that we want to get its equivalent digital value. That will give us the digital representation of that voltage. Now, for 10 millivolts, we're going to say 1023 divided by 5. 1023 is equivalent to 5. What will be equivalent to 10 millivolts? Multiply by 10 exponent negative. What will be equivalent to 10 millivolts? 10 millivolts a digital value of 2.046 will be equivalent to 10 millivolts. But now in a peak, we don't have 0.246. We can have full numbers, 0, 1, 2, 3 up until 2023. So we're going to assume that 10 millivolts is equivalent to a value 2, because that 2.046 is close to 2 if we round it off. So now we will say 10 millivolts is equivalent to a value 2. 20 millivolts, if you calculate, will be equivalent to a value 4. 30 millivolts, 6, and so on and so on and so on. So getting these values, we know that dividing it by 2 gives us the actual temperature, because 6 digital will give us 3 degrees Celsius. So we can formulate and say, whatever the digital value we get, if we divide it by 2, that will give us the actual temperature. But this whole information comes from the fact that each degree change will be represented by 10 millivolts from 0 volts, right? So if our temperature is 2 degrees, LM35 will give us 20 millivolts, and measuring 20 millivolts will enable us to display the 2 degrees, right? So now in the peak, we need, after performing ADC, we'll have a value between 0 and 1023, depending on what the LM35 is giving in as analog voltage. We just need to take that value, divide it by 2, so that it can be temperature, because once we get it, as it is, it's not temperature yet, it is just the ADC results. To convert those ADC results to temperature, we need to divide them by 2. Right, let's go back now to our registers. Now, the AD on registers, the 2 registers, address H and address L, as we discussed them earlier. In my case, I did right justified. Address L will have the 8 least significant bits, and address H will have the 2 most significant bits, and then that will give us 10 bits. Let's just consider a case where I have only 8 bits. The 2 bits are zeros. My number is, or my ADC result is less than 256. Meaning, in the signal here, I'm getting a signal voltage ranging from 0 up to a point where I can get a maximum of 255. Because 255 can fit in one register. Once we go to a value that can give you 256, then address H will be incremented, and address L will have a value again between 0 and 255. When it's greater again than 256, address H will be incremented, and then address L will have a value up until address H has 3 and address L has 255 in it, giving a 1023 10-bit value, right? If I consider only the lower part, why am I considering the lower part? If the aim was to display temperature, for a room temperature, where you have to control a fan and a heater, if you get a result of 255, you divide 255 by 2, you get temperature. The temperature will be 128 degrees, or at least 127 degrees. That means nobody will be alive to monitor that temperature. If the aim of this application is to monitor room temperature, I don't even have to worry about the results exceeding 255. Because if the results exceed 255, I know that temperature is way too much. It's either the system is faulty, it's not measuring temperature correctly, or there's a fire, or there's some sort of heat, and nobody's alive now to even monitor that system. Whether it's accurate or not, that becomes irrelevant. So I'm just going to concentrate on only address L. For that, I'm interested in a temperature less than 128 degrees. And in any case, I think if we look at the data sheet of this LM35, they say you can measure up to 150 degrees. So 128 it's quite enough for my application, or for this application, display temperature in a room and control it using a fan or a heater. If the temperature exceeds more than 100, why bother? Nobody will be alive in that room. I'm not going to bother displaying a temperature greater than 100. So it means I'm only going to concentrate on results where address H is 0 and address L has a value between 0 and 255. So address H is in bank 0. Address H is in bank 0. I can directly read address H here, move file, address H into W, check if the results are 0. The move file instruction is enough to affect what we call the 0 bit. We're going to now discuss the bits of the status register. Bit test file, skip if address L had 0 in it. Skip if status bit 0 is set. Bit test file, skip if set. Status, the bit is 0. If the results are greater than 0, meaning if address L doesn't have, address H doesn't have 0 in it, meaning the temperature is way too much, or the system is malfunctioning, I just don't do anything except go to main, go to remeasure that temperature, go back to main, go to remeasure. But if address H has 0, I can go to address L and try and convert the value there to temperature. Let's see why am I doing this too. Move file, address H into W, and check if status 0 bit is set. This goes back to our instructions. We have a set of instructions that have certain properties. And let's look first at the status register. Where is the status register? I have the status register here. Yes, I have the status register. We have three registers, three lower registers in the status register, named the carry bit, the decimal carry, and the 0 bit. These three bits of the status register can help us identify the results of the arithmetic. If the results were 0, or if there was a decimal carry through when there is arithmetic took place, or if there was a carry. The 0 bit will be set, meaning this bit will be 1 automatically if the results of an arithmetic are 0, or the results of a certain operation are 0, this bit will be set. The carry bit will be set if the results of an arithmetic or an other operation, if the result of that operation affects the 0 bit and the results, there's a carry, that bit will be set. If there's no carry, that bit will be cleared. We will look at the carry bit later on. Let's look at the 0 bit. The 0 bit says the results or the contents of that file are 0, this bit will be set. But which instructions affect the 0 bit? They say here arithmetic instructions or logic operations. Let's look at the instructions themselves. Looking at the list of instructions here, add W to file is an instruction. It affects the carry bit, the decimal carry, and the 0 bit. Add W is an arithmetic. It affects the 0 bit. No, AND. This is the AND, not add. AND is it's a logic operation. It affects only the 0 bit. Most logic operations will affect the 0 bit, of course, but all arithmetic operations will affect all the bits, carry, decimal carry, and the 0 bit. And now, the increment affects the 0 bit, the move file. Move file. If you move the contents of a file, you will see that move file as well affects the 0 bit. If you move a file into W, even if you move a file in a file itself, when you read a file, if the contents of that file are 0, the 0 bit will be set because it says here the move file affects the 0 bit. If the contents of the file you are reading are 0, the 0 bit will be set. If the contents of the file you are reading are not 0, the 0 bit will not be set. It will still be affected. It will be 0, not 1. It will only be 1 if the contents you are reading are 0. Right. So I just used now that property of the move file instruction. Say move file address H into W, read the value in address H and check if it has 0 in it. If it has 0, test here. Status bit 0 will be set if address H results were 0. You read address H, move into W, and then here you say test the 0 bit. If I've read address H and I know move file affects the 0 bit, if the results of address H were 0, when I read this bit will be set. But if this bit is set, yes, the 0 bit is still affected, but the results or the value in address H were not 0. That's what it means. So if the results are 0, you skip. If the results are not 0, it means now your temperature is something way above 128, which is invalid in this application. You can still go and convert it, but for my application or for this, for example, I'm not going to, because it will be a waste of time for me to do that. But it will be a good example if I did do that on how you can convert ADC, right? So if the results are 0, then I know address H has 0 in it. I can only now be concerned on what is the address L. Address H has 0 in it, meaning the value I have is between 0 and 255, which will give me a temperature between 0 and 128. I need to go read address L. Address L is in bank 1. I'm currently in bank 0. Bit set file, status, comma, RP 0, move file, address L into W. I'm reading address L now. Bit clear file, data, comma, RP 0. Going back to bank 0. Bank 0. Here I had to go to bank 1 to go and fetch or read address L. To go read address L value or results. Now, here I just read and ensure that address H is equals to 0. Here I check if address H has 0 in it. And if it has 0, continue. If it doesn't have 0, go back to main. Go to reperforming ADC again. Now, after reading address L, I have my address L value, which can be anything between 0 and 255, which can represent temperature of anything between 0 and 128 or 27 degrees Celsius. I need to convert the results in here to temperature. And remember now, to convert that to temperature, I need to take this, divide by 2. After dividing it by 2, it will be temperature itself. Right. To do that, let's see. We don't have a single instruction that divides when we look at all the instructions available in the microcontroller here. We don't have a single instruction that that can do a divide for us. We don't have a divide. We only have add and subtract, basic arithmetics. Right. But we know we can achieve divide and multiply from those two arithmetic. From add and subtract, we can achieve divide and multiply. What am I going to do? We want to take the ADC results, convert them to temperature, and save the value in the two registers. The two registers, remember, are the tens, which were equated to OX, address 20, and units equated OX, address 21. We can have hundreds if needed, but we only have 27 segments for our application. So hundreds is only here for the conversion purposes. I'm not going to include it in the final program. Hundreds, we can equate it to the next available, 22. Now, I want to convert this ADC results into temperature and move it into those three registers. That's one thing I'm going to do here. Start off at 0. Clear all of them. Clear file, hence, clear file, units, clear file, hundreds. Now, to do a divide, it's not a simple process in an assembly language, as it will be in other higher programming languages. We will have to subtract the number that we want to divide by, we will have to subtract it from the number which we want to divide it from. And then, depending on how many successful subtraction we get from there, that will be the quotient, that will be the divide answer we are looking for. So we're going to have a loop of subtraction. And this loop, I can call it divide, it's fine. I will say here, move a literal value. We have to divide by 2, so I'm going to say move 2 into W, subtract W from file, the file is address L, save the results into address L. Basically here, what's happening is, I'm saying the file which is address L minus 2, and the results, move them into the file itself. Right, I don't know at the moment what is in the file, but I'm saying the contents of the file, subtract 2 and move the results into file. If file, for an example, if file had 10, I would have said 10 minus 2, that will have been equals to 8, and file, the new value into file will be 8. But now, how do I know that the value which I subtracted 2 from is greater than 2? I just need to check my results, were they positive? Because if I say a value minus 2, I'll get positive results if this value was bigger than or equals to 2. If I get negative results, it means the value is less than 2, and I can no longer continue with the subtraction. But if I successfully continue here, I will have subtracted 2 from 10 for the first time. I need to indicate I've subtracted for the first time. Go back to the loop. File minus 2, but now file has now 8 in it. 8 minus 2. The results becomes 6. I check. Are the results still positive? Yes. This is, I've subtracted 2 for the second time. The results are 6, saved into file. Go again back to the loop. 6 subtract 2, the result is 4, still positive. Add that. There's another one. The results are 4. Go back to the loop. So we are going to get this as our quotient depending on how many times did we successfully subtract 2 from this ADC results. That's what the loop has to achieve. And this will actually be our temperature. Let's go and do that. Subtract 2 from address H. Save the result into address H. Now I need to see if the results were positive. Bit test file, skip if the results were positive. I'll say skip if set. status, the bit will be the carry bit. The carry bit. Now we go back and look at the carry bit and what does the carry bit mean in terms of our option register or the status register. I mean, status register, the carry bit is bit 0 of the status register. And for a carry bit there, when you perform arithmetic, let's look back at the instructions that will affect the carry bit first. Subtract is one of them. Where is that subtract? The literal instructions here. Subtract a literal value from W affects all the arithmetic bits. Subtract W from file affects all, including the carry. So this is the instruction we just used. Subtract W from file, and then this affects the carry bit. What does it mean that the carry bit is affected, or that that instruction affects the carry bit? If we have an arithmetic, and in terms of the carry, we have a bigger value minus a smaller value. We have a bigger value minus a smaller value. The carry bit will be 1. That's what you need to know. A bigger value minus a smaller value, or the two equal values, the carry bit will be 1. Once you have a smaller value minus a bigger value, the carry bit will be 0. The carry is an opposite of a borrow. Back in the days, in the primary school, when you were introduced to arithmetic, when they said 10 minus 3, you will first say 0 minus 3, you can't do it. Then you have to go and borrow from the tens, right? And then when you borrow from the tens, that's when the borrow bit. So the borrow will happen when a smaller value, 0 minus 3, happens. A smaller value minus a bigger value, you have to borrow. And when the borrow is set, the carry is cleared. Carry and borrow are the opposite. So if we have a smaller value minus a bigger value, the borrow is set, the carry is cleared. If you have a bigger value minus a smaller value, the carry bit is cleared, meaning the borrow is the carry bit. If you have a bigger value minus a smaller value, the carry bit is set, the borrow is cleared. If you have a smaller value minus a bigger value, the borrow is set, the carry is cleared. So from that principle, whenever you have a big value, in this case, we don't care if it's a 2-digit or single digit. A 10 minus 2, it's a bigger value minus a small value, the carry bit is set. This will be an issue if you have, after at some point, you have 0 minus 2. Then this will mean the carry bit will be cleared. The borrow bit will be set. But there's nothing to borrow, obviously, because we have a 0 there. So as long as we have a positive number or positive results out of your subtraction, then it means you had a bigger number minus a smaller number. The carry bit will always be set. That's the principle we are using here. Say, move 2 into W. Subtract that 2 from the result. If these results were greater than 2, the result will be positive and the carry bit will be set. And if the carry bit is set, we skip. But if the carry bit is not set, we say go to done with temperature. Maybe the conversion is done. But if the results, if the carry bit is set, it means we still have a value that might still be greater than 2. But we need to also pay attention to how many times did we successfully decrement 2 or subtract 2 from address H. I'm going to say, this is for the first time. Increment file, the file that I want to increment is units. Save the result into file. But now, units must hold a value between 0 and 9. Units should never exceed 10. In decimal counting system, you count from 0 to 9 for a single digit. When you go to 10, you actually take the units back to 0 and you increment the tens, right? The unit goes to 0. The units should never exceed 10. then it's no longer units, right? So I'm going to increment units here and check if these units are greater than 9. They should not be greater than 9. So I'm going to say move file units into W. Subtract literal from W. The value is 9. Now, this instruction, you must pay attention. Always W is the one that is being subtracted. When you say subtract W from file, it is file minus W. Subtract W from literal, it is always literal minus W. W is the one that is always subtracted, right? In these assembly instructions. So here I'm saying that 9 minus the contents of W. And the carry bit must be set, meaning 9 should be greater than what is in units. Should always be greater or equals to what is in units. Units should not be greater than 9. So I'm going to say here, bit test file, skip if clear, status, comma carry. Why clear? If it is set, that's what I want. I want to make sure that the carry bit is set, meaning 9 is greater than units. If that is the case, if the carry bit is set, then it's fine. I can go back to the loop. Go to divide. But if the carry bit is cleared, then it means units are now greater than 9. And units should not be greater than 9. Should never be greater than 9. Units must be cleared. Clear file. If the units are greater than 9, skip clear units. But we know that when units becomes greater than 9, we need to increment tens. Increment file, tens, save into file. Now, because we have hundreds, tens should also not exceed 9. So I'm gonna do the same program now, but now I'm checking the tens. The tens should never be greater than 9. Move file, tens into W. Subtract literal from W, the value is 9. Bit test file, skip if the tens are greater than 9. This will be the carry bit. If tens are not greater than 9, it's fine. Let's go back to the divide loop. But if tens are greater than 9, clear tens. Increment hundreds. Increment hundreds, and we know that our value can never exceed 900, so we don't have to check hundreds. Go to divide. This is a division by 2 program in assembly language, saving our results in 3 registers: hundreds, tens, and units. Right. Now, this loop, we're gonna be stuck in this loop until such a point that address L has a value less than 2, meaning we can no longer subtract 2 from address L, meaning we are done with the division. Whatever we have in the results or in temp and units will be our temperature. What is that you want to do with the temperature? I don't know. All right. At this point, if you want to do something with that temperature, you will do it here. And then you will go back to main to perform it again. But now in this program, the main program is responsible for all the time performing ADC. We have just successfully performed ADC. Let me just build this project quickly and see if I can simulate that in the PIC simulator. We haven't displayed it yet. Okay, I don't have the end instruction. Remember, each and every assembly code must end with end. I still have something missing. Here file units, I don't have to specify the destination. Increment tens, here file tens. We build that. Let's see how will this one perform. Load. Where is this one saved? Because it's not 7 segment. Is it? I can't remember where I saved this test program. Okay, in any case, I can just resave it. Or MPLab all in one projects. I see it now. MPLab projects. All in one, this is the one. Right. The rate is still ultimate. Let me just start. Now, you will see here in the ADC, I only made A0 to be an analog input, and my tens, units, and hundreds. Tens, units, and hundreds are registered 20, 21, and 22. Now, if I change my ADC value here, you'll see if I have 5 divided by 2 should give us 2. Where is this problem at? Rate ultimate. Okay, something is happening here. All right, I think I understand what's happening, because I'm moving the results and at the same time I'm clearing them here. Let me use different registers for conversion and use other registers for saving the results. Move file. I'll say I don't want to clear tens, hundreds, and units. I will clear certain registers here. I will name result 0, and then these tens. Just gonna explain what I'm gonna do here now. Result 1 and result. I'm gonna have these two down here somewhere. Units and hundreds. So I'm clearing result 0, result 1, and result 2. I need to specify what are these registers. Just gonna name them there. Result 0 being a register equated to 23. Then I can have result 1 and result 2. So result 2, result 1, and result 0. I'm gonna change these few ones as well. Result. Just gonna change the sequence a little bit, so that I have 100, tens, and units. That's the sequence. 100, hundreds, tens, units, and these are just the registers I'm going to use in the conversion. There will be register 23, 24, and 25. So I'm going to use this to get the results. After I get the results, I can move the results to these registers. So result 0, after performing ADC and converting to temperature, I'm going to move them to hundreds. These ones, I'm going to move them to tens. These ones, I'm going to move them to units. So here I clear result 0, result 1, result 2. Whenever there's a result 0, wherever there's hundreds, I'm going to replace it with result 0. Wherever there's tens, I'm going to replace it with result 1. And then whenever there's units, I'm going to replace it with results 2. So the 3 registers are for getting the results. After acquiring the results, I then have to move results 0 into hundreds, Move file results 0 into W. Then move W to file hundreds. Move file result 1 into W. Move W to file tens. Move file result 2 into W. Move W into file units. So units, tens and hundreds will always be updated by the new temperature from results 0, result 1, and result 2. Then these can be used to display, yet the results 0, 1, 2 are used in the conversion process. Let's see if that will solve my simulation issues here. All right, now load the new program. Start simulation where everything is 0 there. If I make this 10, my temperature has to be 5. Unless if I'm missing something. If I'm missing something, I have to do this step by step. Simulation, step by step. Let's start the simulation to see where I went wrong in the program. For reason 00, go to start, where you go to bank 1. Bit clear status RP1, bit set status RP0, bank 1. Move 1 into uncell register. Only A0 is an analog input, the rest are digital. Move 80 into ADCON 1 register. Go to bank 0. Move value C1 into the ADCON register. ADCON 0 register, selecting channel 0. Perform ADC, wait for the ADC. And as we perform our ADC, let me just see if I'm going to pick up that value. Wait for the ADC to take place. And then once ADC has taken place, we will have to go and check. Move file address L into W. Address L has 0B, which is 11, right? Which is that 11 there. Clear file, result 0, result 1, and result 2. Take 2, subtract it from address H. Oh yeah, that's a problem. You see, subtract from address H. Even a pro like me can still make mistakes. Most importantly is being able to identify where the mistake is. What happened here is, I performed ADC, went to bank 1, get the results for address L, and come with those results back into bank 0. But I cannot access address L while I'm in bank 0. Address L is in bank 1. So when I access address L while in bank 0, I'm actually accessing the wrong address, the equivalent address. The equivalent address, instead of accessing address L because I'm in bank 0, I'm actually accessing address H. And then that's what basically is doing here. Subtract W, address H, whereas in my code I have address L because I'm in the wrong bank. There are two ways I can solve this. I can move 2 into W, go to bank 1, subtract from address L, go back to bank 0, check the results. Or because I've fetched the value here, I can temporarily save it in an extra register. Read the results, go back to bank 0, save it in a temporary register, which will be in bank 0. So I will say move W to file. The file will be ADC results. And I need to go and define what ADC result is. And because I've read address L and saved the value in the ADC result, I no longer have to subtract from address L, but I have to subtract from ADC results. And ADC results will be in bank 0, a general purpose register in bank 0. That will allow me to access it in bank 0. So let me go and say address H can be my last general purpose register equated to memory 26. Right. Let's build this quick build and see what happens when you simulate it this time around. That might have been the only error, could have been one of the errors. Let's just see. High speed, I want to see if I'm going to successfully display. Now, if I have 10 on ADC, my results will be 100 will be 0, 10s will be 0, units will be 5. See, there's 5 there. 100s, 10s, units, right? And if I change this, upper and upper, let's say I make it 30, my temperature has to be 30 divided by 2, which is 50. Meaning 10s will have 5, 10s will have 1, units will have 5. That will be 15. 100s are still 0. To get 125, this value must be close to 256, but not exceed 256. Because I said if it exceeds 256, that will be an invalid reading for my application. I won't even consider it. But if we have 200 divided by 10 divided by 2, let's say 210 divided by 2. That will be 210 divided by 2. This will be 105. There will be 1 in hundreds, 0 in tens, 5 in units, indicating 105 degrees Celsius. Right. Now that we managed to get the ADC program and display the temperature, or get the value for the temperature, I want to display this temperature on a 2/7 segment as it is stated in the ADC, in the initial program that we want to achieve. So going back to the very same old program or old requirement. Now what we just did, we did the ADC and quantify the data, convert it to temperature. Let's now take this program and put it in the main program that we already have. We look at the similarities. We're going to merge the two programs. Going back to the flowchart, start, we don't need this start. It's already there. So we can remove this part. We need to go set up A0 as an analog input. And then we need to go and add that here in the main program. So we say in the two programs, this is where we are setting A0 as an analog input, and this is where we are setting our AD-Con1 to say our VDD and VSS as our references, right? And our results are right justified. We want to do this in bank 1. We take it as it is. Copy this part. It must go in bank 1 in this 7-segment program. We minimize this part, maximize this program. We go to initialize in bank 1, wherever this is in bank 2, this is in bank 1. We can do this at the beginning, it's fine. Or we can do it anyway. Let me do it after the oscillator configuration. I'm moving 1 into AD uncell to make RA0 analog to set up my references. But RA0 must be input for it to be an analog input. So I cannot just clear trace A. A0 must be an input. So instead of clearing trace A, I'm going to modify this instruction. Move 1 into trace A. Move a literal value into W. A binary value that will make maybe at the moment only RA0 as an input. So RA6, RA7, RA6, RA5, whether you make it input or not, it will remain input. I don't even want to try making an output. It can never be an output. So RA7 output, RA6 output, RA5 input, RA4 output, RA3 output, 2 output, 1 output, 0 input. That's the value that I need to move into trace A. Move that value into W, move W to file, trace A. Trace A0 is now an input. A0 is configured as an analog input, and our references are set there. So we have achieved now a certain part. A0 on the configuration, A0, all of that we have achieved. So we can say we are done with this part. No, not completely done, but almost done. Just before we perform ADC, remember we had to set up ADCON 1. And ADCON 0. We had to set up ADCON 0, and ADCON 0 is in bank 0. This we still need to set up. Before we perform ADC, we still need to set up ADCON 0. We copy that part, we move it into the main, but it has to take place in bank 0. So immediately after switching to bank 0, I can put that code there. Once you're in bank 0, move that into ADCON 0. Perfect. Then we are done with that part of ADCON 0. Now we are left with performing ADC, this part. But now this part must come at 1 second interval. That's what the question said. 1 second interval. We did already the program for 1 second interval. We just did the ADC. We just need to take it, put it in the 1 second interval. In the main program, where is our 1 second interval? Our 1 second interval in the main program is here. 1 second. This is 1 second here. This is where we need to add the code that has to take place at 1 second interval. This 1 second interval is the whole code here. This whole code here, where we get our results and we eventually move them into tens, units, and hundreds. That's provided, or with an exception of go to main, because this will be in the interrupt. Instead of going to main, it has to return from interrupt. It will have to return from interrupt. So we're going to remove go to main there. We're never going to have a go to main. And this main will also not be there. But this code will be part of the interrupt. Take this whole code as it is. We put it there to perform ADC for us at 1 second interval. But now this code makes use of general purpose registers. We must have all these registers specified. So we copy all these registers. We come here and we need to check what are the similarities now. We already have tens and units. We don't have hundreds. We already have count. We cannot get rid of count. So let's just paste them as they are. We can say we are going to keep tens and units, but we are going to rename them the way we named them in the ADC program. So hundreds will be address 20, tens will still be there, 21 units will still be there, 22. We still have our count. Units and counts can never share the same register. It's going to be a problem. We can change this. If we want to go by sequence, we can change this to be 23 and all the way down, or we can just take this a bit down and make it the register 27. These are just all general purpose registers. It doesn't matter which one comes first and which one comes last. So this is our program. We try and build it. Let's try and simulate now the main 7-segment program and see if our ADC will change. Remember now, tens and units are displayed by the 7 segment. And we just added the ADC program to the 7 segment. So when we start this, initially it's going to start with 00, with 25, which is what we set initially. But after a second, this has to be a second. That's a thing. The simulator is not running in real time. At the moment, this is actually just over half a second, 0.7, 0.8, 0.9, After 1 second, that will be 0, 0. 0 degrees Celsius. If I take this value down and make it say 84, 84 divided by 2 becomes 41. After a second, that temperature will have to be 41. Remember, this simulation is not running in real time. So that is actually 42. 84 divided by 2 is 42. That is 84 ADC result. Temperature will be 84 divided by 2 becomes 42. If I change that, after a second it will be 70 divided by 2, which has to be 35 degrees Celsius. Right. Due to the time and the length of this video, I wish I could finish the whole example. Now, I need you guys to go and finish this one for me. You now need to go and say, EEPROM, how do you add EEPROM to the whole of this thing? And whenever you get RB0 interrupt, you save the value on EEPROM. Maybe what I can do is this part. What I can add in this video, it is this part where you check the temperature and switch on the heater if it is less than 16, or switch on the fan if it is greater than 27. But you have to go and look at your two registers, the tens and the units, check if or what is the current temperature reading. I might have to do a few more modifications in my ADC program. Why? For me to verify or to check if the temperature is less than or greater than 16, there are two things involved. Because I have tens and units as separate registers, I'm going to have to go and check the tens. Are they greater than 0? If they're less than 0, I don't care about the units, because if the tens are less than 0, obviously the temperature is already less than 16 without having to check the units. If the tens are greater than or equals to 1, if the tens are equals to 1, then I have to go check the units if the units are greater than 16. If the units are less than 16, switch on the heater. If the units are greater than 16 and the tens is equals to 1, switch off the heater. For the fan, I need to go and check the tens. Are they greater than 2? If they are greater than 2, then automatically switch on the fan, because temperature will be greater than 27 if the tens are greater than 2. But if the tens are equals to 2, then I have to go check the units. Are the units greater or less than 7? If they are greater than 7, switch on the fan. If they are less than 7, switch off the fan. Right. That's a very, very hideous process to do. If I don't want to do that, I can have a single register that will have the temperature in it. Because remember, 8-bit register can hold anything between 0 and 255. So I can have 16 and 27 in that one register without separating the tens and the units. So on the divide routine here, whenever I successfully subtract 2 from address, I can increment an extra register, increment file, and I can call it temperature if I want to. But I need to go and declare what temperature is. So temperature is my extra register there. So this temperature register, I also need to clear it at the beginning, so that I start incrementing it from 0. I need to indicate or declare what temperature is. I can do that underneath because that is already 27. Temperature has to be the register in the general purpose section, and that will be register 28. Now, temperature will hold a temperature value, still the temperature value, but not divided in tens and units this time. It will be, if the temperature is 100, you'll be able to display the temperature by using hundreds, tens, and units. But the temperature will hold that register, that value as in a single register value. So I just need to go and play around with this part, the temperature, without having to check the tens and the units individually. So in the main program, it's said here in our application, in the main program, In the main routine, add a program that will check if the temperature is less than 16 or greater than 27. If less than 16, switch on the heater. If greater than 27, switch on the fan temperature. I've made things easy. Have a single register. So I'm going to leave the clear watchdog timer there. It's fine. Now I need to check now in the main routine. Move file. The file is temperature into W. Check if this temperature is less than 60. So I'm going to say subtract literal from W. Value is 50. And bit test file, skip if, I will say what? Need to use, okay, skip if, here, I'll say status carry bit. Here, what am I saying? The carry bit, remember I said, the carry bit will be set when you have a higher value, subtract a small v. And then that subtract literal instruction is actually 15 minus W. If we have a situation where 15 is greater than what is in W, the carry bit will be set. Yes, actually I need to use skip if set here. Meaning if I skip, then 15 is greater than what is in temperature. If the carry bit is set, 15 is greater than what is in temperature. And if 15 is greater than what is in temperature, it means temperature is less than 16 degrees. It is 15 or low, right? Skip if set. Meaning the temperature is 15 or low if the carry bit is set. Yes, that's correct. Now, if the carry bit is not set, it means temperature was a bigger value. I said 15 minus a bigger value. The carry bit will not be set. The borrow bit will be set. So if the carry bit is not set, then it is clear. Then it means temperature is greater than 15. It is 16 upwards. I don't need a heater if the temperature is 16 upwards. Go to check for the upper limit, 27. Go to check for the fan. Or just say for the fan there. But if it is less than 15, I need to go and switch off the fan, read clear file. The fan is which port? The fan, according to our application, the fan is RA2, the heater is RA1. So if it is cold, I need to switch off RA2 and I need to switch on RA1. Read set file, port A, RA1, right? And now I can go and check for the fan. All right, check for the fan. Or actually, I can go to main here because I've identified that my temperature is less than 50. Go to main. Go and check again. Is it still less than 50? Now, check for the fan. I know temperature is greater than 50 because I've just checked here. It's greater than 15. I need to make sure that it is less than 27. So I'm going to say move file again, temperature. Move file temperature into W. Subtract literal from W. Temperature must be 27 or less. Read test file, skip if clear. Status carry bit. If it is set, if the carry bit is set, it means 27 is greater or equals to temperature. Because I'm saying 27 minus temperature. If 27 is greater than temperature, then the carry bit will be set. If 27 is greater or equals to temperature, the carry bit will be set. So if the carry bit is set, I'm not going to skip. What is it that I need to do? I want to go and clear both. Go to, it said there, clear both heater and fan if the temperature is greater than 16 and less than 27. Go to all good. Right. Else, I need to do the opposite here. Switch on the fan, switch off the heater. Bit set file, the fan, bit clear file, the heater. Go to main. All good will be clear both of them. Bit clear file, the fan, bit clear file, the heater. And we are still in the main program. We are still clearing watchdog time. This process won't take 2 seconds. Way before 2 seconds expire, I will have went back to main to clear watchdog time. So in this main routine, we are always going to clear watchdog time. Should the program go to interrupt and get stuck somewhere there, the whole system will reset due to watchdog timer timeout. So building this and testing it has to confirm to us that we successfully achieved part of what we wanted to do. Right, so let me see here. What does this say? Initially, because I said, I am loading 2.5 in the 2 registers, is going to start displaying 2.5. I can read off this 2.5. That's what it's displaying at the beginning. If I remove this 2.5, it can start at 0.0, but at the end of the day, displaying there. It has to change to 35 after 1 second. It's almost 0.8, 0.9. At 1 second, that will have to be 35 degrees. 35 degrees is greater than 27. The heater must be on. The heater is on RA2. Oh, no. 35 is greater than 27. The fan must be on. You see RA2 there. RA2 is on, indicating that the temperature is greater than 27. The fan must be on, which is on RA2. Right. RA2, the fan is on because temperature is greater than 37. Now, if we take this temperature somewhere down to around 42, this will be around 20 degrees, 40. After 1 second, it will update 20 degrees. Both the fan and the heater should be off. So this is a 0.6, 0.7, and so on. In real time, remember, this will be fast enough, so you won't even see this. This is just a limitation to my processor and the simulation process. Now, the temperature is 20 degrees. The fan is off. The heater is off. The fan is blinking there. Need to find out why. But the fan is off and the heater is off. If this temperature goes below 16 degrees, at 28, that will be 14 degrees Celsius. After a second, it's 0.8 now, 0.9. After a second, this will display 14 degrees. The heater has to be on. The fan is off. Right. That is what we have achieved this far. The only part left of this problem, it is the EEPROM. Right into EEPROM when you get RB0 interrupt. It's easy to get RB0 interrupt added, but explaining RB-EEPROM will take quite considerable amount of time. For this application or for this video, let's just end here. I will create a video where we will look at maybe RB0 interrupt and using EEPROM memory, and maybe on that next video I might add a few more other things. Ladies and gentlemen, that's basically the end of today's video on this complicated or almost complicated PIC programming assembly language, trying to identify and show you how do you go about assembly language from a schematic to a flowchart to implementing the solutions step by step, bit by bit. You don't have to do everything at once. You do them bit by bit, you put them together. Bit by bit, you put them together. I know this video is very long, but I hope it becomes useful to most of you. Thank you guys very much. I'll see you on the next video.